Since humanity first looked skyward, we have dreamed of taking to the air, skirting the laws of physics and pushing engineering science to ever greater heights. The power of flight ranks among humanity's greatest achievements. In this episode, we journey from the experimental breakthrough of the Wright brothers to the contemporary icon of commercial travel that is the Boeing 747. And from today's cutting edge of experimental flight, the lightning strike, to tomorrow's vision of interplanetary travel in SpaceX. This is the story of air power. Invisible, but far from intangible, air is the name given to the Earth's atmosphere. Itself a source of power, both devastating and helpful. Air provides resistance to travel. Each time we take to the sky, we are working with air and against it. October 25, 2007. This was the first commercial flight of the largest passenger plane in the world, the Airbus A380.
It's no different to any other aeroplane, whether tiny, medium-sized, large or huge. The aerodynamic principles are exactly the same. But of course, it's rather more interesting watching something that big fly.
Nicknamed Super Jumbo, this enormous craft measures 73 meters long, with a tail fin standing at the same height as a 10-story building. Such is the scale of this craft that 530 kilometers of wiring runs it. Weighing a massive 580 tons, the A380's paint job alone tips the scales at around 650 kilograms. With a plane this huge, one question looms large. Just how does it get airborne?
To achieve that, you need a very aerodynamically efficient aircraft. So you need very large, very efficient engines combined with very aerodynamic design and very efficient and very large wings to generate the lift to keep the aircraft in the air.
Powered by 4 turbofan engines, the unique aspect of the A380's flight is the aerodynamic design of its wings. A design that began as a compromise. The optimal wingspan is 90 meters, well outside airport restrictions.
So had they built it with a straight wing, it would have become too large for basically all the airports in the world. So it would not have been allowed to start or land anywhere just because of its size.
Scaling its wings back to 80 meters, the A380 added unique wingtip fences to maintain an extended aspect ratio without extending length. These distinctive wing fences also serve to reduce a potential hazard of this huge and hugely powerful craft.
When you have an aircraft, the flow around the wing creates something that is known as the wingtip vortex. So the bigger the wing, the bigger these vortices.
An aeroplane's wing generates lift by creating pressure changes in the air. As the wing passes through the air, air moves quickly over the top and slower underneath, resulting in the upward force of lift. A byproduct of this is wake turbulence. With the high and low pressure air left swirling behind the wing to effectively form a horizontal tornado.
These vortices present two primary problems. One, the most important, is that they significantly degrade the efficiency of the wing, its ability to generate lift without generating drag. The other is that they actually present a safety issue for aircraft following behind.
The extended wing fences of the A380 serve to distribute the wake turbulence and drive it upward rather than down. Not a bad result for a wing design that started out as a compromise. with little else by way of compromise, to understand how so many of us can so easily and so comfortably take to the sky, we must look back to more humble beginnings. A little over 100 years ago, in this inauspicious North Carolina field, a truly auspicious event in aviation occurred. It was here, in December 1903, piloting a craft of wood, fabric and wire, that Orville and Wilbur Wright became aeronautical legends. Covering a distance less than the wingspan of a modern 747, this was the first time in history that a powered, heavier-than-air aircraft achieved sustained flight. While the Wright brothers were not the first to pilot experimental aircraft, their fundamental breakthrough was in controlling that flight. It was the Wright brothers' work selling and repairing bicycles which convinced them that a flying machine could be steered and balanced with practice. With the right controls, the Wright brothers believed that learning to fly was like learning to ride a bike. So while their contemporary aviation research focused on building more powerful engines, the Wright brothers worked on steering. And it was the invention of their three-axis control system which was the game changer. This ingenious design, which today remains standard in all fixed-wing aircraft, allows the pilot to steer and maintain equilibrium.
With the fixed-wing design, it was very successful, and from that point onwards, fixed-wing aircraft became the dominant form of aviation.
By the early years of the 20th century, powered flight had become an established technology. The potential of aeronautics for combat, sport, exploration or travel was increasingly recognized around the world, and a period of rapid development was ushered in. A period where the true power was in human bravery. Perhaps no one better exemplifies the pioneering spirit of aviation's golden age than this man, Charles Lindbergh. Known as Lucky Lindy, this former US airmail pilot shot from obscurity to world fame in the course of a single flight. Piloting a purpose-built monoplane, the Spirit of St. Louis, Lindbergh's 5,800-kilometre journey from New York to Paris was simultaneously the first solo transatlantic flight and the first non-stop flight from North America to mainland Europe. Short on funds but high on self-belief, Lindbergh piloted his single-engine craft for a grueling 33.5 hours. Battling storms and navigating by the stars, to land in Paris as a hero on May 21, 1927.
Everyone wanted to meet this daring young man. Even as he posed for these films with members of France's distinguished Aero Club, the entire world was clamoring for its brand new hero.
A feat of both human and mechanical endurance, the achievement brought new public interest to aviation, sparking what was known as the Lindbergh boom. A period in which airmail volume increased by 50% and pilot license applications tripled. For all the bravery and sacrifice of aviation's golden age, the limits of the piston engines that powered these flights were well known.
So after the Second World War, we really saw the rise of the gas turbine, the jet engine as a technology.
Invented years earlier by Frank Whittle for the Royal Air Force in 1921, the jet engine works by firing gas backward in order to thrust aircraft forward. A breakthrough almost as revolutionary as the Wright brothers' first flight.
The attraction of the gas turbine is that you could get even more power out of a given size and a given weight.
Breathing in air through a gas-fired turbine, the jet engine compresses this air through a series of high-speed rotor blades. Forced into a combustion chamber, the compressed air is then sprayed with fuel and ignited. With the expanded gases forced out through the propelling nozzle at the back, the aircraft is thrust forward at high speed. Though still in its infancy, by the end of the Second World War, the turbojet represented the next great leap in aviation. During the war, high-altitude, high-speed bombers were in high demand, leading the English Electric Company to develop designs for just such a plane, the Canberra.
The Canberra is a high-altitude light bomber with great striking power and a speed believed to be over 600.
Featuring an elegant, streamlined design, the Canberra is more notable for the fact that it was the Royal Air Force's first bomber to utilise the power of the newly developed turbojet engine. Coming into service after the war in 1951, the Canberra set a new world record as it flew from Northern Ireland to Canada, becoming the first jet aircraft to make a non-stop transatlantic flight.
As for the trip, that smashed all records as we know. 4 hours, 40 minutes from Aldergrove to Gander, Newfoundland.
Throughout the 50s, Canberras flew higher not only than other bombers, but than any other aircraft at the time. Repeatedly setting world altitude records, the highest a Canberra flew was in its third record-breaking flight, reaching 21,430 metres in 1957. The power of the turbojet combined with its clean design made the Canberra a remarkably versatile aircraft, filling a variety of roles from tactical bombing to photo reconnaissance. Although retired from more than 50 years of military service, Canberras remain in the air today, performing meteorological research and ground mapping work. With peaceful skies, the established power of the turbojet and a surplus of heavy bomber airframes ready for conversion to passenger transport, the end of the Second World War also marked a turning point for civil aviation.
Probably the most rapid period of development in aerospace, certainly in aviation, was that following the Second World War.
One of the first to forge ahead in this new and exciting space was the Vickers Viscount. Employing the gas turbine engine to power propeller blades, the Viscount brought the turboprop aeroplane to the public. But it was the de Havilland Comet that truly burst onto the scene, claiming the glory of being the world's first jet airliner. Manufactured in the United Kingdom, the Comet featured a sleek modern design with 4 turbojet engines buried in the wings, large square windows and a pressured cabin, allowing for comfortable and efficient flying at high altitude. But these commercial pioneers were doomed by a fatal design flaw. If passengers are to breathe while flying at high altitude, a plane's cabin must be pressurized against the low air pressure outside. Increasing cabin pressure while ascending and decreasing it while descending places the structure of the plane under tremendous stress as it expands and contracts with each takeoff and landing. This is what led to the Comet's downfall. A series of tragic and highly publicised accidents saw several of the planes burst apart in mid-flight, resulting in dozens of deaths.
This is the tragic scene of the Comet disaster near Calcutta. Wreckage of the aircraft smashed almost beyond recognition.
After extensive testing, a structural weakness was finally identified around the Comet's square window frames. Suffering metal fatigue after repeated pressurization cycles, the Comets effectively became ticking time bombs, unable to contain cabin pressure at altitude. Despite undergoing a period of extensive redesign, which saw the craft rebuilt with oval windows and reinforced structures, the airline's reputation never recovered. But the quest to conquer commercial airspace did not end, and heeding the lessons from the Comet's design failing, rival manufacturers developed new and improved airliners in quick succession. In the 60s, Douglas Aircraft was the more established manufacturer, and its DC-8, the first commercial transport of any kind to break the sound barrier, took a commanding share of the market. One plane went on to change all that. With its wide body and distinctively humped upper deck, this is one of the most recognizable planes in the air. It is the original jumbo jet, the Boeing 747.
Well, that was a name that was conjured up by the popular press, not by Boeing. There's still people in Boeing who don't like it being called the jumbo jet. It rolls off the tongue, doesn't it? Jumbo equals big, jet, and it's stuck.
Entering service in 1970, the 747 surpassed the DC-8 to take control of the commercial air market by offering vast improvements in performance and comfort.
It revolutionised airline travel, there is no doubt about that. It was able to carry 2.5 times as many passengers as the Boeing 707 and the Douglas DC-8, which were the standard international airliners of the time, which meant that the seat mile costs were lower.
The engine technology was moving from what we called low bypass turbofan technology to this brand new idea of high bypass turbofan technology, which is really the basis of all modern transport engines.
With air entering the turbojet through a fan, the bypass ratio is the amount of air that bypasses around the engine versus the air directed to the engine's core for combustion. All air passing through the initial fan has increased velocity, allowing turbojets to take some thrust from the core and some from the fan. So while combat aircraft use a low bypass ratio, burning more fuel for maximum power, commercial jet engines make use of a high bypass ratio for increased fuel efficiency.
Air travel was still the domain of the richer part of society. But as aircraft size grew, what that meant was that you could bring the cost for the individual traveller down.
There's millions of people who could not previously afford to fly internationally suddenly could. And that was the revolutionary part of the 747. It brought in the current era of mass air travel.
Thanks to the advances in civil aviation, this is what modern air travel looks like today. Often taken for granted, it is the ground-level infrastructure that has enabled the omnipresent reach of air travel. But for all the advances in air power, the forces of nature can still bring us back to Earth. Volcanic eruptions are some of the most awesome natural forces on the planet. Firing clouds of ash high into the air, these particles can enter and potentially stall aircraft engines, creating no-fly zones spanning tens of thousands of square kilometres.
The single biggest improvement in aviation safety was the move from piston engines to gas turbines, because gas turbines are inherently more reliable. The problem is they're designed to ingest air. They're not really designed to ingest particles.
Volcanic ash clouds may be a rare inconvenience for planes, but for helicopters, the risks posed by dust particles are faced every time they take off or land on sandy surfaces. Beyond limiting visibility, sand stirred up by helicopter rotor blades is breathed in by the air intake of the engine.
So while it's not necessarily the belief that a single flight through the dust will result in catastrophic failure of the engine, we're certainly extremely worried that multiple flights will degrade the performance of those engines.
With helicopter engines running at high speeds and high temperatures, once inside, sand particles are sped up and superheated. Captured at 4,000 frames per second, this footage shows the high-speed sand particles slamming against and melting onto the internal engine hardware. The result is an underperforming, unreliable engine deteriorating at approximately 10 times the normal rate, a real risk to the lives of those on board. The solution may look something like this. Currently experimenting with the durable, heat-resistant properties of ceramics, military scientists are hopeful of developing an engine coating that can withstand the ravages of sand. Finding the right chemistry is a process of elimination, but initial results are encouraging, powering helicopters, indeed all aircraft, to operate in an even wider range of conditions. Of course, it wasn't so long ago that the challenge was operating a helicopter under any kind of conditions at all. Unveiled in Nazi Germany in 1936, this is the craft that proved the viability of the helicopter, the Focke-Wulf FW-61. While not the first to achieve rotary flight, the FW-61 easily outperformed contemporary rivals to establish itself as the first truly practical helicopter, providing the basic design that future helicopters went on to develop. Bearing the name of its principal designer, Professor Henrik Fokker, the Focke-Wulf took the fuselage of a light aircraft and replaced the wings with steel outriggers in order to mount three-bladed rotors on either side. These large rotors spun in opposite directions, providing stability. And while the forward propellers on the engine gave the FW-61 the look of an auto-gyro, their shortened blades did not provide power for forward flight, instead cooling the 160 horsepower engine. And this is where Fokker's chief innovation lies. Taking the gas turbine engine that revolutionized aeroplanes, Fokker converted it so that instead of producing jet thrust, the engine powered a spinning shaft which in turn spun the rotors. This is turbo-shaft propulsion, and it is the system still used by the majority of helicopters today. So impressed was the Nazi government with the FW-61 that it became part of their propaganda campaign during the war. Placing Germany's famed female pilot Hannah Wright at the helm, the helicopter was flown for nightly shows in front of large crowds. Such indoor displays could easily have ended in disaster, but thanks to the FW-61's robust control system, Wright, with less than 3 hours practice, successfully flew the craft night after night without incident. Following the war, the most significant advances in helicopter technology took place not in Europe, but in the United States. And there is one man who deservedly takes much of the credit for this, Igor Sikorsky. Born in Russia, Sikorsky was already an established aircraft engineer and pilot when he migrated to the US in 1919. Founding the Sikorsky Aircraft Corporation, he established himself in America as a leading innovator in aviation. And it was this craft, first flown in 1940, which cemented his reputation, the Bort Sikorsky VS-300. Here, the famed innovation concerns a long-standing, or rather long-spinning problem with helicopters, how to stop them spiraling out of control.
And of course, the big problem is that if I have a rotor spinning in the air, then I need to stop the aircraft spinning in the opposite direction.
Newton's third law states that every force has an equal and opposite reaction. And in spinning rotor blades to fly, a helicopter's body tends to spin in the opposite direction. This spinning force, called torque, must be counteracted in order to achieve stability in the air.
And then we need to use things like tail rotors or have more than one rotor to provide that anti-torque to stop the aircraft spinning. And that adds extra weight, complexity, and more points of failure. So these problems have hounded aeronautical engineers for many decades.
Enter the VS-300. With just a single set of lifting rotor blades and a single main gearbox, anti-torque is achieved through a vertical tail rotor. Power is traded off here, with the tail rotor counteracting the main lifting rotors in the name of stability. But the simplicity of its design made the VS-300 worth the compromise. And it's hard to argue with success, with the tail rotor blade configuration pioneered by the VS-300 still seen on most helicopters today. And Of the helicopters today, there is one that casts a long shadow over all others. The Boeing AH-64 Apache. Heavily armed and heavily armoured, the Apache has been compared to a flying tank. Equipped with radar jammer, bulletproof glass, sophisticated sensor equipment, laser-guided targeting, chain guns, and the aptly named Hellfire missiles, the Apache is tricky to detect, difficult to damage, and near impossible to hide from. And to its targets, utterly devastating. But here is where the flying tank comparison falls short. The Apache is also incredibly agile. Modifying the tail rotor blade configuration pioneered by Igor Sikorsky, the Apache employs dual tail rotors, each with 2 blades. More than providing anti-torque force, this setup in combination with a digital stabilization system is optimized to provide remarkable maneuverability, a handy trick when evading enemy fire. A deadly combination of strength, firepower, and agility, the Apache has ruled the skies since it began service in the 1980s, with over 1 million combat flight hours to prove it. But today, a new breed of combat helicopter is rising. This is the Sikorsky S-97 Raider, a compound helicopter designed to provide the one thing conventional helicopters lack: speed.
The limitation of most helicopters is they can't fly very fast, because as the aircraft flies faster and faster, one of those blades is going so slow that the air over it stalls and it no longer produces lift.
On the battlefield, speed is power. And the Raider is built to get into the fight fast and get out even faster. It does this in 2 ways. The first is a coaxial design, essentially stacking 2 counter-spinning rotors on top of each other to eliminate torque without diverting power from their lift and thrust capabilities. Eliminating the need for a stabilizing tail rotor, the Raider is free to bring in its second addition, a pusher propeller out the back to provide even more forward thrust.
There's always been this problem of trying to go faster in a helicopter. We reach a speed of about 200 knots and we can't fly any faster. So these compound helicopters use wings or extra propulsion systems to put less load on the rotor, and by doing that they can actually get faster.
The Raider offers more than pure speed. It aims to revolutionize all aspects of helicopter performance with increased range, altitude, and payload performance. From assault missions to search and rescue, the Raider is customizable to suit a variety of roles as the next generation of military helicopter. With varying degrees of sophistication, helicopters of all sorts have long boasted a particular advantage over planes: the ability to take off and land without a runway. This inevitably raised the question, could a plane do the same thing? Needing a runway is a particular problem for combat aircraft. Air bases represent large, valuable infrastructure, difficult to protect from enemy attack. The need for fighter jets that could operate from improvised bases close to enemy lines was clear, and this was the solution. The Harrier, better known by its informal name, the Jump Jet. Continuing development throughout its lifetime, the first jump jet emerged in the 1960s as a rare success story in the quest for vertical takeoff and landing capabilities. So how did the jump jet succeed where so many others failed?
They had 2 pairs of nozzles, and so in combination, the Harrier could generate thrust at different angles to either short takeoff, manoeuvring in the air, or vertical landing.
Once airborne, the nozzles revolve to push the plane forward. Simple in theory, difficult in practice. Such maneuvers demand tremendous skill on the part of the pilot and tremendous power on the part of the plane. Capable of hovering for just 90 seconds, in this time the plane uses over 500 litres of water to cool the engine. Vertical takeoff is not possible when the plane carries its full loaded weight, so in most cases, a short takeoff is employed. Shortening the runway, ramps are often used to allow the plane to jump into the air, hence the name. In addition to the limitations of their vertical takeoff, jump jets were only capable of subsonic flight.
By going to that large high bypass engine, you are restricting the ability to make the aircraft aerodynamically efficient for supersonic flight.
Nonetheless, the Harrier jump jet was for many years the only plane capable of vertical takeoff and proved its worth in combat.
There was a desire to develop a follow-on to the Harrier that could have all the attributes of the Harrier, of short takeoff and vertical landing, but also be able to fly supersonically. We now see a successful solution, and that successful solution is the F-35 Lightning II, developed by Lockheed Martin.
Today, while the jump jet has retired from active service, its legacy remains as the first aircraft to successfully combine the best aspects of helicopters with planes. At DARPA, the Defense Advanced Research Projects Agency, the search continues for the ultimate aircraft that can do it all. And DARPA is not afraid to think outside the box. This unconventional creation may represent the future of vertical lifting technology. Named Lightning Strike, the unmanned craft has entered into experimental testing. With a hybrid electric system powering its array of 24 thrusters, the Lightning Strike is seeking to set a new benchmark, taking off and hovering efficiently and going faster than any rotorcraft before it. The power of flight takes many forms, and in the 1960s, an ancient technology was reinvented, taking us to new speeds and new heights. It was this technology, 700 years after it was first discovered, that ultimately launched us into the space age. The rocket. Dating back to at least 13th century China, rockets operate on the simple principle of action and reaction. With the majority of their weight consisting of fuel, rockets burn this fuel in order to expel high-speed exhaust, thrusting them in the opposite direction. Simple, but effective. Long used in fireworks and artillery, it was the introduction of liquid fuel instead of gunpowder that brought rocketry into aviation. Compared with air-breathing engines, rockets offer a lightweight source of tremendous power. And it was rocket power that took us faster and further than ever before. This is what the marriage between rocket and plane looks like. The North American X-15. Operated by NASA and the US Air Force from the late 50s to the early 60s, the X-15 was the most successful of the X-planes. A series of experimental aircraft built to test new aviation technologies.
It's essentially a rocket that flew only for about 2 minutes every time, so it had just only fuel enough for that.
And so the X-15 had two primary missions. One of them was to fly as fast as it could through the atmosphere, and that was to look at thermal structural design. The other was to fly as high as it could to the very edge of the atmosphere where you could no longer use traditional control systems.
Almost half a century since it was last in the air, the X-15 remains the fastest manned plane ever flown. With an unofficial top speed of 7,274 kilometers per hour.
That could go up to more than 6 times the speed of sound, so Mach 6. And that holds the record of the fastest atmospheric vehicle that was ever built and flown.
Just how did the X-15 power such astonishing speeds? With this, the XLR-99 rocket engine. This was the world's first large rocket engine capable of increasing and decreasing its power, as well as stalling and restarting. The XLR-99 also provided a frightening amount of power, burning a propellant mixture of oxygen and ammonia to produce a staggering 250 kilotons of force.
It was really a multi-stage system because it was not able by itself to take off from a runway. Instead, it was hung under the wing of a B-52 bomber. And so that B-52 bomber became the first stage. And so that carried it to altitude, and that meant that it already had a head start when it was launched. And then once clear of the B-52, it would light its rocket engines. So it had onboard fuel that it would burn for a very short period, but that was enough to accelerate it all the way up to Mach 6.7. So that's almost 7 times the speed of sound, which is 3 or 4 times faster than a fighter jet, a supersonic fighter jet.
The test flights of the X-15 made history, not only setting a speed record that remains unbroken today, but an altitude record that went unrivaled for 40 years. Of course, the goal of these flights was about more than setting records. It was about research. Over the 199 flights the X-15 undertook, data was collected across all areas of aviation, testing everything from heat shielding and hypersonic flight to the physiological stress on pilots. Considered the most successful flight research program in history, the data gained through the X-15 proved invaluable for the next great frontier of aviation. The quest to fly beyond the atmosphere of the Earth into outer space is a dream as old as humanity. This dream came to a head in the space race of the 1960s.
It was actually the Cold War and the effort to beat the Soviet Union into space and the government funding and the defense backing that really resulted in all the achievements in space.
The Soviets took the lead early, launching the world's first satellite in 1957, and 4 years later, successfully placing cosmonaut Yuri Gagarin into orbit, making him the first man in outer space. But the ultimate objective remained, as outlined by President Kennedy.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
This ambitious goal was tasked to NASA's Apollo program, which began in 1961. And 8 years later, on Apollo's 11th mission, it was 2 men, Neil Armstrong and Buzz Aldrin, who achieved that goal. And what powered the Apollo 11 on its voyage to the moon? Rockets. Really big ones. The Saturn V was the rocket that shot the Apollo 11 into history. Almost 40 years later, it remains the tallest, heaviest, and most powerful rocket ever built. Operating on a 3-stage system, the first and most dangerous stage was simply getting this giant into the air. Packed with 770,000 litres of kerosene and over 1 million litres of liquid oxygen for combustion, the first stage rocket ignites and, with thrust confirmed, is released from the launch tower.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Burning for 2.5 minutes and carrying the vessel to an altitude of over 60 kilometres, the first stage shuts down and separates, falling back to Earth, where it will be burnt up by the atmosphere. Switching to a mixture of liquid hydrogen and oxygen, the second stage rocket propels the spacecraft into the Earth's orbit before being jettisoned. Expelling exhaust to transfer momentum, once in the vacuum of space, rockets are able to work at maximum efficiency, and it is from here that the Saturn V's remaining rocket engine propels the craft towards the moon, with the lunar module making history by touching down on the surface of the moon. Getting to the moon is one thing, getting back safely is another, with the most dangerous part of any space mission being re-entry into Earth's atmosphere.
Anything that comes from outer space typically travels with tremendous speeds, speeds of several kilometers per second.
Traveling through the vacuum of space, there is nothing to slow movement down. But when fast-moving objects, like meteors or Apollo command modules, encounter an atmosphere, the atmospheric gases in front of them are compressed extremely rapidly, causing them to heat up.
They have a several kilometers per second speed by the time they get into the atmosphere. If they were to crash with that speed onto the surface, that would be a major explosion and certainly very unpleasant for all involved.
The Apollo command module has a blunt body design, intended to create high drag and push against as much air as possible.
You have to slow down, and the best way to do this is to convert the kinetic energy, the speed, into heat. And you do this by generating a massive shockwave, because that's exactly what a shockwave does. A shockwave slows the flow down and converts the kinetic energy into temperature.
The shockwave around the Apollo module kept the flaming atmospheric gases from coming into direct contact with the vehicle. Nonetheless, the command module got hot, with its surface reaching temperatures of over 2,700 degrees. Coated with an ablative heat shield designed to melt away, it appeared from below that the command module had caught fire, when in fact it was functioning perfectly. With the shield eroding away from the vehicle, it diverted heat, keeping the history-making occupants safe for their eventual splashdown into the Pacific Ocean. Spurring the desire for further research and exploration of space, the Apollo missions highlighted the need for a more sustainable spacecraft, one that could make multiple trips to and from space. This was NASA's solution.
The Space Shuttle system, an amazing vehicle, probably one of the most amazing machines ever built, one of the most complex machines ever built. One of its prime aims was to bring the cost of space access down.
These were the vehicles that helped build the International Space Station and conduct cutting-edge space research. They remain the only manned space vehicles to have made multiple flights into orbit.
But the Space Shuttle partially achieved reusability. So the orbiter is the only part that goes into orbit and then comes back. There were also some more traditional, large, solid-fueled booster rockets strapped to the side of the stack. Once they had expended all of their solid fuel, they would be released from the stack as it continued towards orbit, and they would fall back towards the Atlantic Ocean. The shuttle continued towards orbit, still attached to its external tank, and so when that tank was empty, when it had expended that fuel, that tank would be released and that would fall back through the atmosphere. And so it would actually burn up during its descent. And so that was not recovered.
Once in orbit, the shuttles provided the crew with everything they needed to live and work in space. And as with the Apollo program, returning to Earth was the most dangerous part of the mission.
The crews that flew the space shuttle were coming through the atmosphere at about 23 to 24 times the speed of sound during their initial re-entry. They were entering 7 to 8 kilometers per second. And so we would probably say that to date, that's the fastest manned winged aircraft.
The angle of re-entry is crucial, with the slightest error causing the craft to break up or skip off the Earth's atmosphere like a stone over a pond. After gaining re-entry, the challenges continue. Now without power, the shuttle must rely on pure aerodynamics to land. Generating lift with its small, swept-back wings, the shuttle slows its descent in a series of S-shaped banking turns before gliding onto the runway for touchdown. The Space Shuttle program was not without tragedy, but the desire for space exploration has not abated. With unmanned satellite and probe technology continuing as a safe and reliable means of space research, the challenge for these crafts is in harnessing an efficient form of power in the vacuum of space. This is the answer: the plasma thruster.
So if you've got a satellite in orbit and it's got a mission life of 2 years, 5 years, 10 years, you need the fuel that you put in that satellite at launch to last that long. Now, with chemical thrusters, you would not be able to make it last that long, but with a plasma thruster, you can because it's highly efficient.
So we're using plasma to generate thrust on a spacecraft. And we do that by converting electrical energy, which you can store very efficiently on a spacecraft, into kinetic energy.
While they may look like the stuff of science fiction, plasma thrusters are actually an incredibly simple and well-established form of propulsion in space. One with the promise of powering space exploration into the future.
Once you're in space and there's no friction and there's no gravity to counteract your movement, you can use these plasma thrusters, which are incredibly efficient, to go to Mars, go outside of the solar system, anything you want to do.
Today, the space race remains as competitive as it ever was. The only difference is that the race is no longer between countries, but companies.
When I was a kid, I read a lot of science fiction, and a lot of the science fiction that had been written envisaged that it would be, the American dream was that private companies, rich individuals, would actually lead the journey into space. Because, that's how America saw itself, as the home of the entrepreneur. Fortunately, in parallel to this thinking, of course, was that we had a number of very successful, very rich individuals who had grown up with the dream of spaceflight that had been inspired by what NASA had done.
With shared goals of commercializing space travel and even colonizing other planets, 3 companies have emerged as leaders in the modern space race. Under founder Richard Branson, Virgin Galactic is seeking to become the space line for Earth. Blue Origin, set up by Amazon founder Jeff Bezos, has even loftier ambitions, with Bezos describing his ultimate goal as having millions of people living and working in space. Also working on big rockets, SpaceX is seeking to reduce the cost of space travel and harbours hopes of colonizing Mars. Such goals could be dismissed as science fiction, but with billionaire tech entrepreneur Elon Musk as CEO, SpaceX is already breaking records and setting new standards for space transport. Through experiments with reusable launch system technology, SpaceX has refined propulsive landings to the point where in 2017, it became the first to successfully relaunch and land the first stage of an orbital rocket. In their race to revolutionize space technology, these companies have set their sights on more than that. This is the forefront of aviation's next great leap. Daring to dream big, the corporate space race is drawing on the funds of its eccentric billionaire backers, but also on the power of the human spirit and its drive to explore and discover new worlds. From the first powered flight to the first lunar landing, the astonishing and rapid progression of aeronautic science has changed the world many times over. Proof that with the power of mastering the air, not even the sky is the limit. Since man first lifted off the ground, the quest for air power has been ceaseless. It is a quest fueled by relentless innovation, brave pioneering and creative experimentation. Not without failure and tragedy, the desire for mastery of the air has carried us ever forward and ever faster. In this episode, we soar from the experimental Bell X-1 that first proved the possibility of supersonic flight to the modern jets like the F-22 Raptor that weaponized it. And from some of the largest craft ever to have taken to the sky to the miniature insect-inspired drones set to redefine the nature of combat. This is the story of air power. The world's most advanced multi-role jet fighter. This is Lockheed Martin's F-35 Lightning II. With three variants, the F-35A is the conventional takeoff and landing model, built for traditional Air Force bases. The F-35B is the world's first supersonic jet capable of short takeoffs and vertical landings.
Rather than having swiveling nozzles that take the flow through the engine and vector it downwards, what it does is it uses a completely separate lift fan that is positioned horizontally behind the pilot and in front of the single main engine.
The F-35C specializes in operating from aircraft carriers, utilizing catapult-assisted takeoffs and barrier-arrested recoveries. All three variants of the Lightning are fast and highly maneuverable. With its array of weapon configurations changing to suit the mission, the F-35 is surprising proof that it's what's on the inside that really counts. Gaining the edge in combat, less through armament and more through information. Information is power, and the F-35 is essentially a flying supercomputer.
One of the key differences with F-35 and fifth generation platforms is rather than having a head-up display system, they actually project the imagery onto the helmet that you're wearing. So you're immersed in sensory information about what the aircraft's doing at the time.
An increase in situational awareness equates to an increase in pilot responsiveness, providing an advantage that can be the difference between life or death in combat. Prior to the integration of computers and the internet with military jets, the quest for superiority in the sky came down to one crucial component: speed.
The military always wants faster, and we generally want speed. If you can go faster, you can get to where you need to be quicker, or you can run away from danger quicker.
Speed, for many years, was pursued as the ultimate weapon in the sky. But one barrier stood in the way: the sound barrier. This is the craft that sought to break that barrier. Nicknamed a bullet with wings, the rocket-powered Bell X-1 was in fact modelled on a Browning .50 caliber machine gun bullet, known to be stable in supersonic flight.
The first proper picture of an object going faster than the speed of sound was taken in 1888 by Ernst Mach, after whom the Mach number later was named.
Questions loomed as to whether a plane could achieve the same speeds and whether a pilot could survive them.
Hoisted into the modified bomb bay of a Superfortress, the Air Force's supersonic XS-1 rocket plane is set for an assault on the sonic barrier at Muroc, California.
Chuck Yeager was selected to pilot this potentially deadly experiment. A role he was so determined to have that he kept secret the 2 broken ribs he'd sustained in a horse riding accident just days prior to the flight. In such pain, he was unable to seal the X-1's hatch by himself. Jaeger nonetheless took to the sky on October 14, 1947.
This was a rocket-powered aircraft designed pretty much along the same lines as people had designed it in the 1940s. Straight wings, which you don't see these days anymore.
Drop launched through the modified bomb bay of a B-29 Superfortress, Jaeger and the X-1, which he'd named Glorious Glennis for his wife, had only a short window before the high-powered rocket engine used up its fast-burning fuel.
Captain Charles Jaeger climbs down into the cockpit of the rocket craft. The release mechanism is tripped, and Uncle Sam's ace in the sky drops clear.
Quickly ascending to over 13,500 meters, Jaeger chased down history, accelerating to the sound barrier breaking speed of 1,100 kilometers per hour. Because sound travels through the air in waves, if an object, such as the X-1, is fast enough, it can catch up to and overtake these waves. As the X-1 closes in on the velocity of its sound waves, these waves begin to pile up in front of it, creating a barrier of sound. The resulting change in pressure as the jet bursts through and overtakes its own sound waves is heard as a sonic boom.
It simply means that if something is flying supersonically, the air will only be changed or will only realize this when this object reaches them. If it's flying subsonically, the air already knows that the object is coming even before it has reached them.
Jaeger's monumental flight was kept top secret until 1948. But once the story was leaked, he became and remained one of the most famous test pilots of all time. Continuing to set speed and altitude records throughout his career, in 2012, Chuck Yeager recreated the X-1's historic flight to mark its 65th anniversary, again going supersonic at 89 years old. The success of the experimental X-1 supercharged the military's need for speed, and soon, rockets weren't the only things going supersonic. A figurative and literal black project from Lockheed's highly secretive Skunk Works division, this plane set the world record for the fastest air-breathing aircraft in 1976 and has held it ever since. The SR-71 Blackbird. Designed for stealthy reconnaissance missions over foreign countries, if the Blackbird ever found itself in trouble, the plan was to simply outrun the threat using its supersonic afterburners. An afterburner injects fuel into the engine exhaust to burn the remaining oxygen in the exhaust stream.
The expansion of the gas through the nozzle accelerates the fuel out the back, and Newton's law says there's an equal and opposite force that pushes the aircraft forwards.
For most fighter jets, the afterburner gives added power for short bursts of 3 to 5 minutes. For the Blackbird, its engines were designed to run continuously in afterburner for hours, only slowing for mid-air refueling. But high speeds come with a cost.
At full speed, it takes something like 100 nautical miles to turn around because its aerodynamic lift, or your ability to actually turn, is so restricted at the very high speeds.
The Blackbird was engineered to withstand the stresses of sustained supersonic flight, the main one being heat. For the Blackbird, surface temperatures could reach over 480 degrees Celsius.
When you fly very fast, the friction between the flow over the vehicle and the structure of the vehicle produces heat through friction. And this heats the vehicle up, and that challenges the structural design. Things start to distort, to fail when they get hot.
Constructed largely from titanium to provide durability at high temperatures, in order to accommodate the metal expanding as it warmed up, gaps were left between the body panels, meaning fuel would leak when the Blackbird was on the runway. It was only when airborne and warmed by friction that the metal would expand and the gaps would seal. Gathering mission-critical intelligence during the Cold War for the 25 years the Blackbird was in service, over 4,000 missiles were fired at it. Thanks to its superior speed, not a single one hit it. Speed is useful in avoiding a fight. It is also useful if you're looking to pick one. And if you throw range, maneuverability, stealth and weapons into the mix, you get a craft you do not want to mess with. You get the Lockheed F-22 Raptor. Considered the world's strongest combat aircraft, while much of the Raptor's capabilities remain classified, it's no secret that it has speed to burn. The F-22 is the first American fighter jet capable of achieving supersonic speeds without the use of fuel-guzzling afterburners. Known as supercruising, the Raptor achieves this through a highly aerodynamic design and a highly powerful set of Pratt & Whitney F-119 engines. Producing more thrust than any other fighter engine, the F-119s allow the Raptor to fly faster for longer and with less fuel. In carrying less fuel, the Raptor can carry more weapons. And by deploying these weapons while supercruising at high altitude, the Raptor provides its munitions with a helpful boost, increasing their range by about 50%. Beyond its supercruising abilities, the Raptor is also super maneuverable. Using a thrust vectoring system to direct its engine's exhaust up or down, the Raptor can pull off high-speed maneuvers that are the envy of its enemies. But it was a lack of enemies that ultimately defeated the Raptor. With a hefty price tag and a period of relative peace, the Raptor program was cancelled in 2009, with less than 200 ever produced. The military were not the only industry to see the potential of supersonic flight. And commercial airliners raced to develop a passenger plane that could match fighter jet speeds. While the Concorde may be first to mind, this is the plane that won the race, the Soviet-built Tupolev Tu-144. Codenamed Charger, the Tu-144 first flew on New Year's Eve of 1968, beating its Anglo-French rival by 2 months to claim honours as the first commercial supersonic plane ever flown. Jokingly labelled the Concordski by its European competitors, the design of the Soviet-built craft did bear a striking resemblance to that of the Concorde.
Engineering problems tend to drive you to similar solutions. And so the Russian aircraft was similar in many ways. It potentially had more engineering issues though.
Both the Concorde and the Tu-144 feature distinctive hinged noses, dropping downward during takeoff and landing so that the pilots could see in front of the high-angled plane. And while both planes employed a delta wing design, never since used on commercial aircraft, the Charger had a unique added feature, its retractable forewings. With its delta wings offering limited lift at low speeds, the Charger's forewings, or mustache canard as it was known, was used to boost the plane's lift during takeoff and improve handling during landing. While the Tu-144 was first in the air and the first commercial transport to exceed Mach 2, at the Paris Air Show in 1973, disaster struck. The high-profile fatal crash delayed production of the Charger for years.
Even though it did see commercial operation within the Soviet Union, it never came close to the success of the Concorde.
Speed has always been the big selling point of a civil airliner. It's universally agreed that the next step should be supersonic flight.
The product of a successful English-French partnership. This is the iconic craft that truly took supersonic travel to the masses. The Concorde.
An amazing machine that really has yet to be surpassed in its success as one of only 2 supersonic transport aircraft.
With its first commercial flight in 1976, the Concorde made the technological feat of supersonic travel an everyday reality. Across its quintessential route between London and New York, while a subsonic carrier might take around 8 hours, the Concorde did it in 3.5. Travelling beyond the sound barrier, the Concorde was subjected to tremendous pressure. Due to the intense heat of such high speeds, the Concorde's frame was designed to allow expansion of over 25 centimetres. The key to unlocking supersonic flight for a plane as big as the Concorde was here. The distinctive delta-shaped wings, though they came with a compromise. Only generating limited lift when flying at low speeds, for the Concorde to get off the ground, a high-speed takeoff was necessary. And even more nerve-wrackingly high-speed landings were required in order to control descent. But once the plane got up to speed in the air, the delta wings were more than worth it. When a plane breaks the sound barrier, the shockwave boundary folds back toward the plane. With a conventional wing design, the shockwave would strike the plane at the wings, creating drag. The delta wing's thin, streamlined profile avoids the shockwave entirely, enabling efficient and stable supersonic travel.
There are not many aircraft really that come anywhere close to the Concorde and be able to sustain such high speeds for such long periods of time. And so that comes down to this idea of an aeropropulsive balance, that the faster you fly, the more drag you produce. And so you need very, very good aerodynamic design to minimize that drag. But then to overcome that drag, you need very efficient engines. So you need the combination of powerful, efficient engines with very efficient aerodynamic design. So we see that in the Concorde.
In service for 27 years, the Concorde made just under 50,000 flights in its lifetime, allowing some 2.5 million people to experience flight beyond the speed of sound. There was controversy in the form of noise complaints from the sonic booms it generated, but ultimately, it was economics that led to the Concorde's retirement in 2003, with the supersonic plane not profitable against the carrying capacity of its larger, slower rivals.
There is a lot of work currently underway through various engineering companies around the world, designing what will follow the Concorde. What we are likely to see in the pretty near future is the emergence of operational supersonic business jets.
Incorporating advances in aerodynamics and jet engines with lighter, cheaper composite materials, startup company Boom Technology aims to have a fleet of mini Concordes by 2023. Set to fly faster and more efficiently than their iconic predecessor, Boom proposes ticket prices on par with traditional carriers, making supersonic flight more accessible than ever before. Ever since Chuck Yeager first piloted the Bell X-1 to supersonic speeds, experimental aviation has been faced with a question: how to get from supersonic to hypersonic.
Hypersonic is going much faster than the speed of sound. So there's a barrier at the speed of sound where you start to form shockwaves. And supersonic is faster than that, and hypersonic is more than 5 times faster than the speed of sound.
Today, this is the cutting edge of hypersonic flight. NASA's X-43A.
The X-43 is a supersonic combustion ramjet engine, or a scramjet engine. And that's an engine that's designed to burn fuel faster than the speed of sound.
A single-use unmanned craft, the X-43A broke its own previous record of Mach 7 on November 16, 2004, when it reached a staggering speed of approximately 10,600 kilometers per hour, close to 10 times the speed of sound. To reach such speeds, the X-43 is first carried into the air by a customized B-52 Stratofortress. When it is drop-launched, the X-43 is attached to a Pegasus rocket booster which fires up to carry the craft even higher and faster.
Launch. Sequence reset. Ignition. Ignition.
After leveling out at an altitude of over 30,000 meters and already flying at 5 times the speed of sound, the X-43 switches to its own scramjet engine and leaves the rocket behind.
Separation. Fuel is on.
Unlike a turbojet that compresses air with a rotating compressor, a scramjet uses forward velocity and aerodynamics to achieve the same effect without moving parts. In the X-43, the craft itself is integrated with the engine, with the front designed to scoop up oxygen, forcefully compressing the supersonic airflow before combusting it with hydrogen fuel. The expanding hot gases are expelled through the aft of the plane, which acts as a nozzle to accelerate the exhaust, generating its tremendous thrust.
Normally, if you want to go really fast, like you want to go into space or something, then you would use a rocket. But a rocket has to bring its oxygen with it. If you have an engine that can use the oxygen in the air, then you don't have to bring it with you and you can carry more payload.
Generating tremendous thrust without the need for onboard oxygen, the X-43 is proving scramjet technology.
I think we'll see scramjets with military purposes, so perhaps for fighter aircraft, certainly for missiles, and potentially for access to space.
While the power of speed remains prized in the air, size can also be an asset or a liability. The longest flying machine and largest by volume, the LZ-129 Hindenburg launched to great fanfare in Germany on March 1936.
The Hindenburg, Germany's latest and greatest dirigible, rises from Friedrichshafen on her first demonstration flight.
It was massive. It was 245 metres long. That's 3.5 times the length of a Boeing 747. It was huge.
Powered by 4 reversible Daimler-Benz diesel engines, the Hindenburg gracefully made 17 round trips across the Atlantic.
Complete success crowns the Hindenburg's first South Atlantic crossing, and the biggest airship ever built lands safely at Rio de Janeiro.
Heralded as the future of air travel, today it is remembered as one of the world's biggest air disasters.
It had a fatal flaw in that it was filled with hydrogen rather than an inert gas like helium, which is what you would use today.
Nearing the fatal end of her first Atlantic trip of the season, the Hindenburg approaches the mooring mast at Lakehurst. Scarcely 100 feet above ground, the giant airship with her framework encasing 7 million cubic feet of inflammable gas is being carefully maneuvered towards her hangar, when suddenly...
May 6th, 1937, the Hindenburg explodes into flames while docking in New Jersey. With a simple spark of static electricity, 36 people lost their lives, marking the end of the airship era. But the quest for scaled-up air transport continued. And during the Second World War, the need to fly troops and material across the Atlantic resulted in the largest aeroplane ever constructed, the Hughes H-4 Hercules. Built by the larger-than-life businessman and aviator Howard Hughes, the construction of this flying cargo ship was made more challenging by US wartime restrictions on metals, resulting in it being built entirely from wood.
It was intended to be a flying ship, and it was designed at a time when conventional shipping across the Atlantic was being sunk in very high numbers by German U-boats.
Howard Hughes' flying boat has a wingspread of 320 feet, and that gives you some idea of its size. Howard Hughes himself checked the controls before the first tests were carried out at Long Beach, California.
Powered by 8 Pratt & Whitney Wasp major engines, the largest aviation piston engines ever mass-produced in the US, the craft made just one flight in 1947. The unannounced decision was made during a taxi test, and with Hughes himself at the controls, the airboat reached an altitude of around 20 metres for a single minute.
The aircraft remained in ground effect during that whole flight, which meant it was still being supported by the effect of the wings on the ground or the water underneath. So we don't know whether it would ever have flown like a conventional aircraft, but it flew. He did it. That was Howard Hughes. That's the way he operated.
The Second World War drove demand not only for large-scale transport, but for heavy bombers. One of the largest operational aircraft during the war, the B-29 Superfortress was also the most expensive US weapons project of its time, outspending the Manhattan Project that developed the first nuclear bomb by more than $1 billion.
The B-29 Superfortress is highly advanced for its time. It had things like tricycle undercarriage, which was unusual in those days. It had pressurization of the cabin, which was most unusual in those days. Remotely controlled defensive guns. It was a bit of a technical marvel. At the end of the day, it was the aircraft that ended the Second World War.
At 2:45 in the morning, August 6, 1945, Colonel Tibbets takes the Enola Gay down the runway into the air.
Flying under 4 Wright duplex Cyclones, the most powerful radial engines ever made in the US, the B-29 cruised at high altitudes, beyond the range of ground defenses. The heaviest production plane of its day, the B-29's ultimate power was in the nuclear weapons it was equipped to carry. And in the final stages of the war, this ultimate power was used, with 2 separate B-29s dropping 2 separate nuclear bombs on the cities of Hiroshima and Nagasaki.
At 9:15, the bomb is dropped. The aircraft banks away at high speed.
Killing an estimated 129,000 people, these controversial and devastating bombings forced the surrender of Japan and remained the only use of nuclear weapons in warfare. Another Boeing giant designed to carry nuclear armaments, the B-52 Stratofortress, is a Cold War relic that refuses to die. First flown in 1952, the Stratofortress was built as a high-altitude nuclear bomber. Designed to fly above the range of ground-based defence systems and deliver its nuclear payload anywhere in the world. As the Cold War hotted up, the B-52s became the only bomber that mattered. With Operation Chrome Dome ordering nuclear-equipped B-52s to fly the Soviet Union's borders 24 hours a day for 8 years running.
The B-52's main role is a strategic bomber. Its capability has developed over the years from one of dropping just unguided dumb bombs. It's now able to carry and deploy a full range of guided weapons.
Scheduled to remain in service until at least 2040, the B-52 Stratofortress will be flown by the great-grandchildren of its original pilots, proving this huge craft's unparalleled power in terms of sheer longevity. Powered by the rising property of heated air, or by harnessing gases less dense than air. Throughout the long history of ballooning, the technology has remained simple, while the achievements have become increasingly impressive. In 1906, the world's first international air race, the Gordon Bennett Cup, was established for balloons, a race that continues to this day.
Paris was the starting place of the recent balloon race. Yes, balloon racing has begun again, in spite of all the more recent inventions and advances in aviation.
First reaching the stratosphere in 1932, balloons continue to take us higher, with new benchmarks constantly being set. And balloons, the first form of air power, continue as a significant force today, carrying us ever further. High-flying and efficient, balloons have been incorporated into NASA's space research program, where they have proven to have a range of advantages over rockets.
High-altitude space balloons are a way where you can do space-like environments cheaply, more efficiently, and they often end up being a test bed for bigger experiments that eventually do go into space.
Comprised of a thin film of polyethylene, about the thickness of a sandwich wrap, building a balloon is hardly rocket science. And it's a lot cheaper. With a balloon launch attracting far less red tape than a typical rocket launch, this old-school technology is once again at the cutting edge.
I think the biggest thing that I'm impressed by is that they fly. They look so flimsy. I mean, the material it's like cellophane. You would think that how could this thing survive the harsh environments of going all the way up 30, 40, 50, 60 kilometers, staying for that long, and then just gently land on the ground.
Capable of lifting over 3,500 kilograms, NASA's balloon program uses two different types of helium-filled balloons to transport scientific payloads into the atmosphere.
So we have what we call zero-pressure balloons. So these are really enclosed balloons, but because the higher you get into the sky, there's lower pressure, so gas expands. But by going really high, air eventually escapes and eventually seep out, and you come straight back down.
Superpressure balloons, on the other hand, are completely sealed, holding a relatively constant gas pressure in the face of changing temperatures.
It acts like a bladder, so it's like a balloon inside a balloon. You have hydrogen in one shell, helium in the other, and you expand and contract that inner bladder, and that allows you to keep in a stable altitude, in a stable orbit, or a stable position of the Earth. And these can go for hundreds of days or even months.
The scale of these scientific balloons is truly enormous. With a size well over 1 million cubic meters, a fully inflated balloon can easily contain a sporting stadium. The quest for new sources of power in the sky is unending. With its array of photovoltaic cells and battery storage units, the Swiss-engineered solar impulse is powered purely by the sun. And it is already breaking records. Among them, the first circumnavigation of the world by a piloted solar aircraft. The aim now is to repeat the feat without stopping. Quieter, cleaner, and more efficient, this flying solar panel has greater ambitions than just breaking records. Seeking to move flight beyond limited fossil fuels to a source of endless renewable energy. In certain areas, the power of the pilot is every bit as important as the power of the plane. Almost as old as flight itself, aerobatics and air racing today is codified into a popular spectator sport. Stunts such as these test not only a plane's maneuverability, but a pilot's nerve and skill. A successful aerobatic pilot needs to manage the G-forces that their bodies are subjected to, as well as the physical stress on the body of the plane. The stunt plane of the military world. The Mikoyan MiG-29 is capable of aerial feats that would be impossible with regular aerodynamic controls. Designed as a multi-role fighter capable of operating from improvised airfields at the front lines of the Cold War, the MiG-29 first took to the sky in the late 70s. Codenamed Fulcrum, this was one of the last cutting-edge jet fighters produced before the collapse of the Soviet Union, and it continues to serve in the Russian Air Force today. With twin Klimov RD-33 turbofan engines spaced widely apart to provide additional lift, the lightweight Fulcrum boasted excellent acceleration with a top speed exceeding Mach 2, faster than its American F-16 rival. But the MiG-29's real claim to fame is its super maneuverability, proven by the demanding move known as Pugachev's Cobra.
This is a rapid pitch-up manoeuvre, so the aircraft is flying along, pitches its nose up even beyond the vertical, and then can recover that back down and resume normal flight, which for a conventional aircraft is just impossible. The aircraft would stall and lose altitude very rapidly.
The Fulcrum's wing shape generates a vortex of air over the front edge.
That vortex is generating quite a bit of force. It's maintaining the lift at an angle of attack of the aircraft well beyond where a normal aircraft would stall.
For all its agility, the MiG-29 was undermined by some notable shortcomings. A lack of modern electronics meant that its pilots had limited situational awareness. And with a range of less than 1,500 kilometres and no in-flight refuelling ability, the Fulcrum was a multi-role fighter in name only, primarily serving in defence or frontline support. Despite these limitations, with a reasonable price tag and recent upgrades to address some of its shortcomings, this Soviet-era jet continues to serve in militaries around the world. As jet fighters engaged in increasingly risky maneuvers at increasingly high altitudes, the question of how pilots could safely bail out came to the fore. This is how it was answered. Riding a high-altitude balloon into the stratosphere, Colonel Joseph Kittinger performed a series of experiments throughout the late 50s and early 60s as part of the US Air Force's project to develop safe ejection equipment for high-altitude pilots. Kittinger's job was to jump. Wearing a pressurized suit to prevent his blood from boiling at the extreme heights, in 1959, Kittinger stepped out from the balloon's gondola to perform the world's first stratospheric space dive. It was a first, and nearly a last for Kittinger, as an equipment malfunction caused him to black out, with his automatic parachute saving his life.
Our bodies are built to be on the Earth with gravity and relatively normal temperatures, not to go through extremes and in extremes in only a few minutes. So you're really pushing your body to the limit when they do these jumps.
Indomitable, Kittinger returned to the stratosphere twice more. And it was during the ascent for his final jump in 1960 that the seal on his right glove failed. Kittinger kept quiet as his hand swelled to twice the normal size and lost function.
These stratosphere jumps have a huge team of medical doctors monitoring every part of it, because when they land, they need to know how to treat them. Are they deprived of oxygen? Have they had hypothermia? Are there pressure problems? Can they see? Are they going to have a heart attack?
Kittinger persevered, ascending to a manned balloon altitude record of 31 kilometres before again taking the plunge.
I had made the jump 1,000 times in my mind, so when it came time to go, I was ready to go. I reached 614 miles an hour. I free fell for 4 minutes and 36 seconds. And then once the parachute was open, it took about 10 minutes to get to the ground. And when I landed, my team was there, and we were happy campers.
Man is capable of remarkable feats in the air. But today, a new trend in aviation is seeing the pilot taken out of the plane. Today, we are witnessing the rise of the drones.
Pilots get tired, they need to be fed, they need to go to the toilet, whereas a robot machine can just keep flying. As long as there's power and there's fuel, it can just keep going and going and going.
Unmanned aerial vehicles, or UAVs for short, have been in the sky in various forms since 1916. With advances in technology, these flying robots are now a genuine power in the sky and are only becoming more powerful. With a range of sizes and capabilities, drones are used in everything from agriculture to racing. It is the military that has produced the greatest leaps in drone technology. And this is the result. General Atomics MQ-9 Reaper. The first unmanned hunter-killer designed for long endurance missions and high-altitude surveillance.
The Reaper is powered by a 900 horsepower turboprop engine. That enables it to fly for 14 hours at heights up to 50,000 feet.
More powerful than previous models, the Reaper can not only fly further, but can carry a heavier payload. With a wealth of advanced sensors in its bulbous nose, and weapons including laser-guided bombs and Hellfire missiles, the Reaper is the world's deadliest drone. Connected by a satellite link, the Reaper is always monitored by a pilot, analysing the images the craft provides and issuing commands from the safety of a ground control station thousands of kilometres from the conflict. And progress continues with Northrop Grumman's X-47B. The first strike fighter-sized drones to achieve carrier-based launches and recoveries.
It has a unique capability that it can be launched and recovered to a ship at sea, which means the force and the power of that vehicle can be projected to anywhere in the world.
The X-47B has also demonstrated the first autonomous aerial refueling of an unmanned aircraft, setting the stage for entire fleets of carrier-based UAVs. A new generation of military drones are already taking to the sky. And with the pilots staying grounded, the machines have gotten small.
We're going to see drones that are smaller, and we're going to see drones that are smarter.
Instead of people, these micro drones can carry communications payloads such as cameras, able to penetrate spaces inaccessible to conventional UAVs. They offer applications ranging from counterinsurgency to search and rescue. Or they can be weaponized. Released from Air Force bombers, clusters of explosive drones are set to replace the cluster bomb. Staying aloft to perform aerial maneuvers, they adopt a holding pattern before diving down at the right moment and self-detonating with enhanced precision. The new aerial arms race is smart and small, and within a generation, the nature of conflict could be rendered almost unrecognizable. But going small poses a big problem. At this level, everything we know about powered flight ceases to work, and a new understanding of fluid dynamics is required. An understanding provided by nature. Essentially, the smaller you go, the more resistance air provides. And on the insect scale, the air is a thicker, stickier medium. Moving through air at this level is more like swimming than flying. And this is where fluid dynamics comes in. When an insect flaps its wings, a swirling vortex of air is formed, creating an area of high pressure to push the wing up from below. Before flapping down again, the wing rotates to create a backspin force, pulling a faster stream of air over its top surface. As the wing hits the vortex from its previous stroke, it generates additional force that can be directed up or down by the angle of the wing, a principle called wake capture. While humans are yet to manufacture a machine that perfectly mimics insect flight, the power of wake capture is being used to create a range of insect-inspired machines.
Nature as inspiration is particularly useful for these really small scales of flight because it provides a way to overcome this scaling problem and say we can more efficiently generate flight at these small scales.
While nature has had millions of years to perfect animal flight, humans have just had a few hundred. In returning our focus to the natural world, our understanding of flight and the unique properties of air is being revolutionized. And the skies are set to become a very different place. To travel the land, one thing is prized above all else: speed. Since the fast production methods of Henry Ford put the world on wheels, speed has influenced every aspect of the car. And the car has literally shaped our world. In this episode, we surge from the once ubiquitous utilitarian Model T to the muscular V8 stylings of the Mustang, and from the jet-powered supersonic thrust to the electric game changers of Tesla. This is the story of land power. While only 29% of our planet is land, this is where we all live. And that 29% still equates to more than 92 million square kilometres to get around. 92 million square kilometres of mountains, ice, deserts, jungles, and everything in between. In order to efficiently traverse this vast terrain, often rugged and often inhospitable, man has evolved to walk upright. And the evolution has not stopped there. Today, this is where the evolution has taken us. The latest and greatest vehicle from a long-standing auto manufacturer, founded on the belief that nothing is too beautiful and nothing is too expensive. This is the Bugatti Chiron.
I believe it's really, they're in a league of their own. There's no one close to it for that level of hyper car.
The Chiron is the worthy successor to Bugatti's Veyron, the fastest street-legal car in the world, with a top speed of over 430 kilometres per hour.
The Veyron is a marker in the sand. It is the world's fastest car, and it will probably stay as the world's fastest production car for a long, long time to come.
The Chiron uses very similar technology to what was developed in the Veyron, and it's sort of a last hurrah for non-hybrid hypercars, where we have a nice big engine with 4 turbochargers and everything's mechanical.
With its speed electronically capped at 420 kilometres per hour, the Chiron, as the company likes to put it, brings beast to a very high level of beauty.
In terms of what they are, there's no electric motors or anything like that, it's still raw brute power.
While its speed may be capped, the Chiron's 16-cylinder W configuration engine delivers a 25% performance increase over the Veyron, thanks largely to its 4 double-powered turbochargers.
They use W16 engines, meaning that you have W cylinder arrangement, and that can accommodate up to 16 cylinders in it, which is crazy.
With the engine mounted centrally in the car, more weight is placed over the rear tyres, increasing both acceleration and sensibly braking. Weight is otherwise kept to a minimum with a light and highly aerodynamic carbon fibre body. Defined by its sweeping C-shaped curves, these design features are integrated into the performance of the car, optimizing airflow to an engine that gulps a massive 16,000 litres of air per minute. Directing airflow is vital for speed, but in a car this overpowered, it's also necessary to keep it from flying off the road. Along the flat aerodynamic underbody of the car, a series of forward flaps adjust their angle at high speeds to keep downward pressure on the front tyres. The slit-raised wing at the back does the same for the rear wheels and serves as an air brake. With a multi-million-dollar price tag and taking an average of 6 months from construction to customer delivery, Bugatti releases around 70 Chirons per year, placing them among the world's most exclusive production vehicles.
No one will ever build anything like that ever again. It's a very iconic car in that sense. It's a one-off. You'll never see anything like that ever being produced, not on a mass scale. So it is a very, very special car.
More exclusive, though less luxurious, automobiles of various designs could be seen on the roads as far back as the early 19th century. The car has no single inventor. Rather, it's an evolution of the sum of an estimated 100,000 patents from dozens of inventors around the world. Experimenting with various forms of power, the first horseless carriages ran on steam, gas, or electricity, until one innovation steered them in a particular direction. Built by German engineer Nikolaus Otto in 1876, the Otto cycle was a compressed charge internal combustion engine that went on to define the dominant power source of automobiles for more than a century.
An internal combustion engine works by converting chemical energy into heat energy and then into mechanical energy. So by igniting a fuel-air mixture, we can increase the pressure within the combustion chamber, which drives the piston of the engine down. Now that downwards motion of the piston in turn rotates the crankshaft, and that crankshaft gives us rotational energy, which we can then use to drive the wheels.
While the concept of internal combustion engines had been around for many years, even after the technology was proven, it would be years before it was put into a car. To Carl Benz, we owe the first practical mass-produced automobile, the Benz patent motor wagon of 1885. The three-wheeled construction featured a four-stroke engine of his own design, with an advanced electric ignition system and rudimentary steering. The motor wagon went on to become the first commercially available automobile in history, aided by a unique marketing campaign.
So internal combustion engine, the idea was there for hundreds of years, but then it was first commercialized and tested in a real vehicle by Mr. Benz and his wife.
Unbeknownst to Carl, his entrepreneurial wife Bertha took the vehicle and their two sons on a 100-kilometre journey to visit her mother, famously notifying her husband by leaving a note. This journey was the first long-distance drive, proving the viability of the automobile.
And that, by record, is the first driven internal combustion engine powered vehicle in the world history.
As cars continued to grow in practicality, they remained costly contraptions owned only by the rich. More than any other, one man and one car changed that forever. Henry Ford and the Model T. Born to a Michigan farming family in 1863, from an early age, Henry Ford showed an aptitude for mechanics. And after turning 16, he left farming life behind to pursue a career in engineering. Establishing the Ford Motor Company in 1903, Ford's vision was to manufacture inexpensive cars using skilled workers earning good wages. He did this by developing the assembly line technique of mass production. Installing lines of conveyor belts in his factory, Ford workers, who were paid a generous $5 a day, were at the height of production able to churn out more than 300,000 Model Ts annually. Offered to the public in any choice of colour, so long as it was black, the reason behind Ford's famous pronouncement was that Japanese black enamel was the only finish capable of drying fast enough to keep up with his production method. Model Ts could be put together in as little as 93 minutes, and these savings in time translated to financial savings for the customer. Because of Henry Ford and the Model T, car ownership in the US became affordable to the many rather than the few. And by 1918, half of all cars in America were Model Ts. Started via hand crank, the Model T's four-cylinder 20-horsepower engine reached a top speed of about 70 kilometres an hour, more than enough on the largely unpaved roads of the day. Utilitarian in appearance, uncomfortable to drive, and incessantly rattling, the Model T's many shortcomings were the source of many affectionate jokes. Nonetheless, this affordable mass-produced car is credited with powering a social revolution by providing independent transport to the masses. Ford would also be at the forefront of the next great revolution in automobiles, the V8 engine. First patented in France in 1902, the V8 engine was initially more common in speedboats and aeroplanes before it found its now iconic place in cars. The V in the V8 comes from the angle at which the 8 cylinders are mounted on the crankcase. Split into two opposing banks of 4, the cylinders drive a common crankshaft. which, as in a standard engine layout, converts the piston's linear energy into rotational motion that is transferred through the gearbox to the wheels. With the overlapping power strokes of the 8 cylinders largely eliminating unwanted engine vibrations, the V8 is an inherently balanced design. But the V8's principal innovation was that it generated more power without an increase in size.
By increasing the size of the engine, then you can produce more power. It is just a question about how to fit that certain volume that's large into a limited space.
Introduced in 1932, the Ford Flathead V8 was the first affordable, mass-produced V8 engine. The Flathead revitalized and redirected the Ford Motor Company. This engine whetted the appetite of power-hungry consumers, and the design of cars changed radically to keep up. From the V8, a new generation of car was born. While fast, overpowered cars had been produced before, it was in 1960s America that they went mainstream. With petrol cheap, the economy strong, and the youth market lusting for fast, sexy vehicles, the era of utilitarian transport gave way to a period of tire-smoking excitement in the form of muscle cars. These affordable small to mid-size cars, with their powerful V8 engines, could be driven for everyday street use, or pitted against each other in formal or informal drag races. With automakers competing for supremacy on the racetrack as well as the sales chart, the motto became, race on Sunday, sell on Monday. And this was the sales success story of the 1960s, the Ford Mustang. Coming onto the market in 1964, the Mustang, with its low price, good looks, and long options list, took America by storm. Although not initially marketed as a muscle car, the Mustang, with its optional range of gutsy V8 engines, certainly had the power to qualify. Instead, this high-performance compact created its own market category, the pony car. A huge factor in the Mustang's initial success was its low price point, owed to the fact that it shared much of its engineering with an existing Ford product, the Falcon. But it hardly mattered to the public. The Mustang offered enough stylistic points of difference to be its own car. Ranging from a 164 horsepower model to the high-performance version boasting 271 horsepower, the sales sensation of the 60s, the Mustang created a trend with the muscle car market that other automakers were bound to follow. Arriving fashionably late to the pony car party, Pontiac's 1967 Firebird made quite the entrance. Built with the specific purpose of competing with the Mustang, Pontiac had a little over 2 years to design and engineer the Firebird, which in car-making terms equates to a mad dash. To meet its deadline, the Firebird, much like the car it was striving to beat, started out by borrowing parts from existing vehicles, namely those of the Chevrolet Camaro. Chevrolet and Pontiac were both brands owned by General Motors, and both the Camaro and the Firebird were aimed at cutting into the Mustang's dominance over the muscle car market. Like the pony car it was made to compete against, the Firebird was offered with 6-cylinder engines as well as a range of V8s. And the V8s were by far the most popular. While the Firebird stirred the same levels of passion in its drivers, it never met the sales levels of the Mustang it was designed to tame. Remembered with a fondness beyond sales charts, the Firebird remains a much-loved product of the competitive spirit that characterized the muscle car era. Coming to an end in the 1970s, the period of muscle cars was short-lived, but their influence has remained strong and fed into other types of car cars like the Dodge Viper.
The Dodge Viper is an all-American action supercar. It is traditional, big engine, big, loud, brash car.
Some engineers at Dodge had the great idea of stuffing the biggest engine that they had lying around into the smallest car they could fit it into, and the Dodge Viper was born. It's a point-and-shoot muscle car that will go incredibly quickly in a straight line.
First roaring onto American streets in 1992, this heavily muscled sports car and its voluptuous stylings pay loving tribute to the muscle cars of the early 60s. In a period where the prevailing trend was toward efficient, conservative cars, this gas-guzzling extrovert was a throwback to a different time. The chief selling point of this impractical vehicle was that it offered what few others in the more sensible 90s car market could: brute power.
It's got an 8.3-litre V10 engine, which is literally out of a truck, but they've transformed it into a performance car engine that just is brutal.
Recruiting the expertise of supercar manufacturer Lamborghini, which was owned by Chrysler at the time, the Viper delivered a rating of 400 horsepower at 4,600 revs per minute, numbers almost unheard of in the early 90s.
It produces about 480 kilowatts in its top spec, which is probably about 5 times the average small hatchback, and around the same sort of power as most of its supercar rivals.
Delivering great gobs of power to its extra-wide Michelin tyres, there was plenty of traction, and the Viper stuck to the road like the snake it was named after. Car lovers could not get enough, and the trend-bucking Viper, with its nostalgia for the muscle cars of a previous generation, was a top-selling instant classic. Before production vehicles were built and sold with race car power, the race for pure speed was long in the running. During the pioneering days of speed racing in the 1920s and 30s, few figures captured the public's adoration quite like Sir Malcolm Campbell. Holding the land speed record 9 times during his life, as well as setting 4 water speed records, the British-born motorist received a knighthood for his contribution to the field. Racing in a series of several cars he named Bluebird, the fastest of these was the Campbell Railton model, built in collaboration with British automotive engineer Reed Railton. A design of the modernist 30s, the Campbell Railton Bluebird featured a low rectangular cross-section, spanning the full width of the wheels for reduced drag. Its distinctive tombstone radiator grille could be closed with a movable flap, briefly enhancing the aerodynamic profile during record runs. Powered by a Rolls-Royce V12 engine, the Bluebird made record-breaking runs across the hard-packed sands of Florida's Daytona Beach in 1933 and again in 1935. Clocking what was an unprecedented top speed of 445 kilometers per hour. Campbell knew the car was capable of more. Believing that a lack of traction on the sand was holding the Bluebird back, Campbell's quest for speed led him to the Bonneville Salt Flats of Utah. Here, on September 3rd, 1935, with his young son Donald watching on, Malcolm Campbell set his last land speed record of 484 kilometers per hour. Dying in 1948, Sir Malcolm Campbell was a rarity among the speed racers of his day, not only with his long list of successes on land and water, but for the fact he died from natural causes rather than in a crash.
Well, Dad, I'm mighty glad you reached the 300, but I felt sure you'd do it.
Right, old chap, I'm very pleased too. But I reckon you've had a real good time whilst you've been over here in the States, because everybody's been so awfully kind to you, haven't they?
They sure have.
Following in his father's racetracks, Donald Campbell set land and water speed records throughout the 1950s and 60s. While a generation before, his father Malcolm had been the first to break the 300-mile-per-hour mark on land. It was Donald's great ambition to go even faster, with his sights set on breaking 400. This was the vehicle that he hoped would do it. the Bluebird Proteus CN7, the first car to be powered by a gas turbine engine, an engine that up until this point had only been used in airliners. Drawing air into the engine through the car's open nose, this painstakingly streamlined vehicle was thought to be capable of over 800 kilometres per hour. Returning in 1960 to the site of his father's last record in Utah, Donald crashed during a test run at around 580 kilometres per hour. Thanks to the tremendous structural integrity of the vehicle, he survived.
I have survived the fastest crash that mankind has ever survived.
Despite being intensely superstitious, Donald Campbell's bad luck continued. With the car completely rebuilt, a more promising racing ground had been located on the dry lake bed of Lake Eyre in South Australia, a site that had gone without rain for 9 years. Shipping car and crew to the remote location in 1962, the heavens opened up and the lake was ultimately flooded to a depth of 3 inches. Finally, after 18 months of waiting, Donald made his courageous record-setting attempt on the still damp track. He achieved his goal, scraping past the 400-mile-per-hour mark and setting a new land speed record of 648 kilometres per hour. Never getting the chance to race on land again, Donald died 5 years later during a water speed attempt. From the early 60s, the land speed record climbed steadily higher, with the title of fastest man on Earth being traded back and forth between a handful of drivers. Californian Craig Breedlove claimed and reclaimed the honour several times before putting an end to things, at least for a while, in 1965. Using a surplus General Electric J47 engine, common in military aircraft, Breedlove's first record-breaking runs were not accepted by the International Automobile Federation because his vehicle, the Spirit of America, had 3 wheels instead of 4. After a near-fatal crash in 1964, the undaunted Breedlove returned a year later with the 4-wheeled Spirit of America Sonic 1. Powered by a superior J79 engine, he held the official land speed record for all of 5 days before it was surpassed. But the very next week, Breedlove responded with a new record of 966 kilometres per hour. This time, the record would last 5 years before being broken in 1970. To claim it back, Breedlove set his sights on going faster than the speed of sound. But he was not alone. This was the vehicle that Breedlove was up against, the Thrust Supersonic car, SSC for short. Designed by a British team headed by Richard Noble, who himself set the land speed record in 1983, this jet-propelled car had the express purpose of not only breaking the record, but breaking the sound barrier.
If you want to go faster than the speed of sound on land, your problems actually are larger than in air, because you have the solid boundary, the Earth, on which you're traveling, and that means there's a very small gap between the moving object and the Earth.
Propelled by a pair of afterburning Rolls-Royce Spey 202 jet engines, the same used in F-4 Phantom fighters, the Thrust SSC produced an awesome 110,000 horsepower, making it the most powerful car ever built. Designing a car this powerful was one thing. Finding someone to sit behind the wheel was another. With a select few capable of the job, a rigorous testing process arrived at this man, Royal Air Force fighter pilot Andy Green.
It's like a man walking on the moon. It's the 4-minute mile. It's climbing Everest. It's something that nobody's ever done before. It's something that no team has ever done before.
Green's challenge was immense. unable to house steering gear at the front of the vehicle due to aerodynamic restrictions, the thrust SSC was steered via its asymmetric rear wheels. Whether such an unusual system was viable at the speed of sound was uncertain.
From the aerodynamic point of view, make this very dangerous. You have this very slim cushion of high-speed air sitting underneath the vehicle, and there is a serious chance that this vehicle would be lifted.
Or if the nose were to dip, the car would drive itself into the ground. Everything hinged on having a perfectly neutral aerodynamic profile. Even if everything performed perfectly, the question of what happens when a land vehicle pierces the sound barrier remained unknown. There were fears that the resulting shockwave may derail or destroy the car, along with its driver. Nonetheless, in October of 1997, Andy Green and Craig Breedlove squared off in the Nevada desert to find out. Sadly for Breedlove, he never had his opportunity. With his latest Spirit of America suffering engine damage during a test run, he was forced from the contest and could only watch from the sidelines as Andy Green and the Thrust SSC took to the sands. 50 years and 1 day since Chuck Yeager and the Bell X-1 rocket plane first broke the sound barrier, Andy Green and the Thrust SSC joined the club, blitzing along the desert at a top speed of 1,227 kilometers per hour. This was the first time a car had gone supersonic. The record stands to this day, but it is not safe from attempts to break it. And Andy Green and the Thrust team are among those seeking to go faster still. Henry Ford is quoted with saying that auto racing began 5 minutes after the second car was built. With formalized racing events dating back to the emergence of gasoline-fueled cars, the racetrack has a long history of serving as a competitive testing arena, spurring continual improvements across all areas of vehicle performance.
The only race of its kind in the world, there were 49 starters in this year's Grand Prix.
More than any other, the world's oldest active endurance race, Le Mans, is credited with inspiring technology that has translated into consumer cars. Held annually in France since 1923, Le Mans has been called the Grand Prix of endurance and efficiency. Racing for 24 hours, competitors strive to cover the most distance around a circuit that mixes public roads with professional racetracks. With modern distances easily exceeding 5,000 kilometres, Le Mans tests not only a vehicle's speed, but its fuel economy, reliability and safety.
Le Mans is an interesting race in that the engines have to be designed for both power and efficiency. Because it is such a long race, going for 24 hours, if your engine is inefficient, you will be making a lot of fuel stops. And obviously, while you're stopped refilling your car, your competitors are going to be driving past you.
The long, fast straight known as the Mulsanne has fostered developments in aerodynamic performance. And with the unique safety rule that requires cars to be switched off while being refueled, hardier vehicles that can restart multiple times are de rigueur. Despite the emphasis Le Mans places on safety, deaths have occurred here, with the greatest tragedy being this crash in 1955, resulting in the death of 80 people. In response to the disaster, Le Mans, as well as other races around the world, enhanced its safety measures. But as safety standards improved, so did the power of cars, with vehicles adopting more extreme designs to attain more extreme speeds. Vehicles like the Porsche 917. The development of this now legendary car came about due to a rule change in motorsports that allowed for a new class of cars to enter endurance racing. With engine capacity capped at 5 litres, Porsche began work on a smaller engine version of its 908, and in just 10 months, the 917 was built.
Definitely the 917 broke all records and really made people have a look. Absolutely amazing car.
The car, in spite of its often garish 1970s paintwork, is today considered one of the greatest race cars ever made, and was even immortalised in film, starring alongside Steve McQueen in the 1971 movie Le Mans. But the 917 did not achieve instant greatness. In early models, the power of its 12-cylinder engine, capable of going from 0 to 100 kilometres an hour in 2.4 seconds, exceeded the vehicle's handling, and Porsche had a hard time finding drivers willing to pilot what was considered an accident waiting to happen. And at the 1969 Le Mans, the accident did happen, with driver John Wolfe losing control of his 917 and dying in the resulting crash. But Porsche persisted, and chief engineer John Horsman found the solution to the 917's problem. In studying the splatter of dead bugs over the vehicle following test laps, he noticed that the insects were concentrated on the bodywork, not the tail. No bugs meant no airflow, and therefore, no downforce. At high speeds, a race car's tail, or wing, is designed to do the opposite of wings on a plane.
Race cars tend to have downforce, so that is, they have aeroplane wings that are upside down that press the car into the surface, which increases the pressure that the tyre has to deal with, and they get very hot, so the slick tyres tend to be very strong construction and very, very sticky rubber compounds to keep the race car on the track.
With its lightweight aluminium frame and fiberglass body, the key to making the Porsche 917 into the dominant race car it became was in perfecting the design of the tail. Adding shorter, more upswept fins provided a clean flow of downforce-inducing air over the rear wheels. With a dramatic improvement in the car's handling, Porsche suddenly had a race winner on its hands. And in 1970, this car provided the German manufacturer with its first win at Le Mans. The following year was even more impressive, with the car again taking out Le Mans as well as 8 of the 10 races for the World Trophy, cementing the 917's enduring legacy as one of the most powerful street-legal race cars. With technology proven on the track, a class of cars emerged featuring the best performance and design the auto industry had to offer. Supercars. The term supercar has been used in the car market since the 1920s. Today, this is what it means. This is the Lamborghini Huracan. With its V10 engine delivering 610 horsepower, the highly powerful, highly luxurious Huracan can go from 0 to 100 in a blistering 3.2 seconds, securing it the honour of Supercar of the Year upon its release in 2014.
So it sounds amazing. I suppose the magician's back at the factory. A lot of it's with the engineering, with the exhaust and the manifolds and the way the sound gets delivered.
Using aerodynamica Lamborghini Attivia technology, ALA for short, the Huracan bends air to its will. On the front, a horizontal splitter blocks air from flowing beneath the car, maintaining downforce on the front tyres. When downforce and the drag associated with it is unnecessary, a pair of flaps open in a split second, allowing air to flow through for improved aerodynamics. On the back, air intakes can direct airflow above or below the rear wing, again balancing downforce with drag. The wing itself contains a hollow chamber, allowing airflow to be directed internally to either side. When cornering at high speed, the ALA system directs airflow, and therefore downforce, to the inboard half of the wing, balancing the load on the rear tyres.
The Lamborghini Huracan engine is a V10, which means that there are 10 cylinders in a V configuration, 5 on each side. The engine can produce 610 horsepower, which is equivalent to the amount of work 610 horses could do over 1 hour.
With its high power and high performance, the Huracan is an instant classic of the elite supercar genre. Not all supercars are created equal. And even in this rarefied world, it is possible to go one better. The best of the best. The top 1% of supercars are classed as hypercars. Cars like the Lykan Hypersport. Made by the United Arab Emirates company W Motors, this is the first hypercar of the Middle East. And carrying a price tag well in excess of $3 million, it is also among the most expensive production cars ever to go on sale. With a twin turbocharged flat 6 engine positioned behind the driver, the Lykan produces 750 horsepower. Going from 0 to 100 in a breakneck 2.8 seconds. The car's top speed is just shy of 400 kilometers per hour. With only 7 Lykans produced, they are among the most exclusive cars on the market, even by hypercar standards. Much about this enigmatic and excessive vehicle remains a mystery, including how many have been sold. Though it is safe to say that this is an extremely powerful car, owned by extremely powerful people. With supercars continuing to develop new technology and improve performance, for a vehicle like the Lykan to attain hypercar status, it must be at the very forefront of engineering and design. But the bar continues to be raised, and what is extraordinary today may be commonplace tomorrow. While it may be some time before diamond-encrusted headlights are standard, the innovations that have come from cars have the power to change the world. Literally reshaping the land, roads allowed cars to reach their full potential. And as cars came to travel faster and more frequently upon them, safety technology needed to accelerate to keep pace. First performed in the 1930s, crash testing quickly became a popular means of investigating a vehicle's structural integrity. With crash test dummies introduced in the late 40s, the impacts on a car's occupants became better understood, and this form of testing led to a suite of safety innovations. As the shortcomings of simple lap seatbelts were demonstrated, Volvo developed the now standard 3-point seatbelt. Rather than patenting the technology for profit, it was made freely available in the interest of saving lives. Airbags, unpopular at first, became more effective with improvements in seatbelts and are standard today. And as cars have become safer in accidents, the trend has shifted towards accident prevention, with a host of smart technologies designed to monitor driver performance or take over driving altogether. Just as it was in Ford's day, the greatest influence a car has is not the car itself, but how it is built. And today, vehicle manufacturing is on the cusp of a revolution, more world-changing than Ford's assembly line.
3D printing is a revolutionary engineering tool. It has the ability to manufacture quite complex shapes, layer by layer or in a blown system. So things like design complexities are not an issue anymore. Virtually anything can be manufactured using 3D printing.
Not only can 3D printing change the way we make cars, it can change the cars we make. With current methods needing to stamp out big pieces of metal into shape, cars are designed around parts that are mass-producible, not necessarily optimal. 3D printing offers a means of making optimal components mass-producible. With the freedom to add extra material to stress points for enhanced strength, or leave gaps to reduce weight, 3D printed vehicles are both stronger and lighter. But that is just the start. By customizing every detail of every car part, the possibilities of 3D printing are endless. Doing away with inflexible, mile-long assembly lines, small-scale factories will be empowered to produce an endless array of cars. With no need to retool an entire factory of machines, a 3D printer can go from making a truck to a small car with no downtime at all. Major manufacturers already use 3D printing to produce prototypes of vehicles that will later be produced en masse using assembly line methods. And with vehicle manufacturing one of the most environmentally damaging industries, the waste-reducing benefits of 3D printing promise a sustainable future for the auto industry. For cars to be truly sustainable, a new source of power is needed. Harmful to the environment and human health alike, the emissions from fuel-burning engines are increasingly being regulated by governments around the world. And as oil decreases in abundance, oil-derived fuels are increasing in cost. Fortunately, cars from their very inception have a history of running on alternative power. Hybrid cars decrease their dependency on fuel by incorporating an additional power source, typically electricity. Running an electric motor alongside an internal combustion engine, hybrids seek to improve fuel efficiency as a means of decreasing pollution and running costs.
Hybrid vehicles can be configured in a number of ways. The electric motor and the petrol motor or diesel motor can complement each other. They can work in parallel or they can work in series. So there's a lot of flexibility when it comes to designing a hybrid vehicle.
The first car to combine an internal combustion engine with an electric motor was constructed in 1898 by a young Austrian doctor with the familiar name of Ferdinand Porsche. 100 years later, the hybrid is back in vogue.
You basically have two power sources in any hybrid engines. The way they work is you have power split device right in the middle. And you have internal combustion engine running when it's needed to generate electricity, or directly linked to the power shaft and make the vehicle move. And this power split device sitting in can be used to control, either use that mechanical motion to generate electricity so that there's some energy can be stored in a battery, and then the electricity can be used when it's needed.
Electric engines also have the advantage of acting as self-powering generators, capturing energy that would otherwise be lost and converting it to electricity. This is particularly evident in regenerative braking. In conventional cars, brakes produce friction with the brake rotors in order to slow down, dissipating the vehicle's kinetic energy as heat. Regenerative braking slows the wheels by putting the electric motor into reverse. While running backwards, the electric motor is functioning as a generator, producing electricity and feeding it into the vehicle's batteries for later use. Economical and environmentally friendly, the long-known energy-saving technology of hybrids is today steering performance cars in new directions. A plug-in hybrid, the BMW i8 delivers near supercar performance with the fuel economy and emission standards of a compact vehicle. Marketed as the world's most progressive sports car, BMW claims the i8 is a vision of the future. And as the world's top-selling electrified sports car, they may be right. Chargeable via an ordinary wall socket, its high-voltage lithium-ion battery bank is maintained at an optimum operating temperature by an innovative cooling system. The turbocharged 1.5-litre three-cylinder petrol engine produces a healthy 230 horsepower. Sitting above the rear axle, the combustion engine takes a back seat to its electric counterpart.
BMW i8 approach, it's a little bit different. Your vehicle will be operated solely by AC motor and internal combustion engine. It does not produce direct power supply to your power shaft, but it's more or less generating electricity, and then the generated electricity is used to run the AC motor. So the AC motor is the core element to produce power.
Obviously, the more motors you can have delivering power at any one time, the faster that car can go. It can be configured to just drive the wheels with the electric motor and use the engine as a generator. It's like carrying a power plant around with you in the car.
With an electronically limited top speed of 250 kilometres per hour, the i8 provides performance with impressive fuel efficiency and minimal emissions. With a choice of 4 driving modes, at one end of the spectrum, Sport mode makes the most of the petrol engine for maximum power. At the other end, eDrive relies solely on the electric motor, which can take the car for around 37 kilometres without using a single drop of fuel. The i8's highly aerodynamic design and its lightweight body, featuring carbon fibre reinforced plastics, adds to the efficiency and sports car performance. This is an energy-efficient, environmentally friendly vehicle that does not skimp on the power and fun of a traditional sports car. The need for a new source of power, reliable, sustainable and affordable, has brought us to the cusp of a new era in automobiles. One car maker is counting on it. Tesla is both an auto manufacturer and a renewable energy company. Specialising in battery storage, it is the marriage of car maker and power provider that has seen Tesla lauded as the world's most important car company. Named in honour of Nikola Tesla, the genius Serbian engineer who invented the induction motor and alternating current power transmission, Tesla builds electric cars that don't just measure up to conventional vehicles, but outperform them. And with a maverick CEO in the form of Elon Musk, Tesla is using a business model all its own to make different cars for a different future. Tesla's first car, the Roadster, released in 2008, was the first high-performance all-electric car. Going from 0 to 100 in 4 seconds and able to travel more than 320 kilometres on a single charge. Constantly improving, the more recent Model S, with its ludicrous mode, goes from 0 to 100 in a staggering 2.7 seconds.
Essentially, the ludicrous mode on a Tesla just runs the electric motors up to their maximum rated power, which is inefficient, so it creates a lot of heat and it drains the batteries very quickly, but you can go fast. You can go very fast.
The key to this speed is the instant torque provided by the electric engine.
Torque is essentially the strength of an engine, or how much force it can put out, whereas power is the product of that force and the speed that the engine is turning at. So how many times per second that force is being applied is what gives us power.
The power advantage of an electric motor is its access to full torque from a standstill. Needing to force air into the engine for combustion, conventional engines have to build torque over a period of acceleration. For electric motors, the torque is produced not from the explosion of igniting fuel and oxygen, but from an electrical charge that winds the motor. Therefore, torque is produced the instant electricity is applied. Where once the internal combustion engine set a course for cars to follow and for innovators to build upon, today, the electric motor is set to overtake it. Tesla is building toward a world where electric vehicles will have levels of ownership beyond those of the Ford Model T. And as the revolutionary mass manufacturing techniques of Henry Ford put the world on wheels, now the radical possibilities of 3D printing are disrupting the established order. As we race ever forward, the story of how cars evolved in the past offers telling insight for their evolution in the future. The automobile has changed the world we live in. Colossal networks of roads have reshaped the land, carving paths between cities and towns themselves, built around the needs of cars. But land-going vehicles are not confined to tarmac. And the true freedom and mobility afforded by automobiles is in their ability to take us beyond. In this episode, we venture from the rough and ready revolution of the military Jeep to the smart tech-driven future promised by the BMW Motorrad, and from the heavy-duty powerhouse of the Caterpillar Series 7 to the flying cars turning science fiction into science fact. This is the story of land power. When it comes to all-terrain vehicles, this one truly lives up to the name. Taking inspiration from the legendary mountaineering Sherpas of the Himalayas, the Russian-built Sherp ATV takes on just about anything nature can throw at it.
I have never seen anything like it in my life. It's just amazing. And that's technology, like, comes so far in that type of vehicle these days. And so they can build an ATV that can go anywhere, basically. I'm just gobsmacked by what they can do now.
Extremely manoeuvrable, the Sherp's lever steering mechanism controls the speed of its oversized wheels on both sides of the vehicle, allowing for skid steering and turning in place. The patented tyres also let the Sherp do this. The buoyancy of its tyres and their paddle-like tread allow this mini monster truck to swim at an impressive 6 kilometres per hour, jumping in and out of the water with ease. This amphibious car is all but unstoppable. Running on ultra-low pressure, the tubeless tyres mould around obstacles, allowing the Sherp to climb obstructions over 2 feet tall. And self-inflatable, they can be adjusted for optimum performance over varying terrain. Sitting proud of the vehicle, the custom tyres are so large that in top-of-the-line models, they house additional fuel tanks. Drawing just 44 horsepower from its Japanese Kabuta 1.5-litre turbo diesel engine, the Sherp maxes out at around 45 kilometres per hour, commanding the land less through engine power and more through sheer ruggedness of design. With a durable polymer coating for extra toughness and a smooth protective underbody, the Sherp is built to withstand a tremendous amount of punishment. Should a problem occur, ease of maintenance has been factored into the design, with the transmission simply bolted onto the tub-like steel frame. The company also boasts of the vehicle's high survivability, claiming it can continue driving on just 2 wheels. A go-anywhere car without equal, the Sherp was built to serve workers in the most demanding environments on the planet. Nonetheless, with its adult-sized Tonka truck appearance, a sense of fun here is inescapable. Perhaps unsurprising, given that the fun and freedom of recreational off-roading has its origins in some very no-nonsense vehicles. Vehicles like the Unimog. Few automobiles can boast the enduring success and celebrated versatility of the Unimog. Even fewer can claim to have emerged from such bleak circumstances. Entering production in 1947, the first of these universal motor vehicles featured all-wheel drive and a flexible frame integrated with the suspension, aspects that were unique at the time.
Unbelievable climbing, the angles you can get them at is just amazing. Amazing off-road abilities, big, high, once again, high centre of gravity, but great for troops, carrying heavy loads, that type of thing.
Carrying power takeoff points and machinery mounts, the early Unimogs were put to use operating saws in forests or harvesters in fields. In the 1950s, with Mercedes-Benz taking over manufacture and industrial restrictions on Germany easing, the Unimog expanded beyond the farm, adding more powerful engines and more sophisticated technology, including different attachment systems for a wider range of jobs. The Unimog's potential was realised as a vehicle that could not only go anywhere, but could do anything, and the evolution has continued to this day. Adaptable to an endless array of purpose-specific customisation, Unimogs have been put to use in industry, military, emergency services, and recreation. A combination of car, truck, and tractor, the Unimog has proved itself as the ultimate all-rounder, and an indestructible living legend. Hailed as the godfather of modern-day four-wheel drives, the US Army's Jeep was designed for a very specific wartime purpose, but went on to have a much wider influence in times of peace.
Way back then, they were pretty ordinary, pretty rough to ride in, not the sort of thing you'd want to be taking your family around in.
The first of its kind, this tough and agile go-anywhere vehicle laid out the essential blueprint that lightweight 4x4s would follow for years to come. The origins of the term Jeep remain unclear, but the development of this iconic vehicle stemmed from the vision of the US Army and the coerced collaboration of several car companies. Anticipating entry into the Second World War, the US military knew it needed to modernize. Putting out hundreds of tenders for equipment and machines, one such tender called for a command reconnaissance vehicle, the vehicle that would become the Jeep. With the Army setting exceedingly strict demands for power, performance, weight and size, none of the original prototypes they were presented with made the grade. But three companies came close: Ford, Willys and Bantam. And through the grudging, possibly illegal, sharing of their designs, the combination of all three companies' efforts resulted in the Jeep. Core to the Jeep's design is a separate chassis carried on leaf springs over live beam axles, allowing power transfer to all four wheels. While the solid beam axle prevents independent movement of the wheels, meaning that the motion of one affects the other, their mechanical simplicity provides a crucial off-road advantage: durability. And durable is exactly what the Jeep proved to be, fulfilling its envisioned Second World War role as a reconnaissance vehicle, and doing just about everything else the Army asked of it. Versions of the Jeep remained in service until the early 1980s, and the Jeep had a lasting appeal in peacetime too, beginning the world's love affair with recreational off-roading.
World-renowned for its reliability is the Land Rover. In this British factory, the Land Rover is manufactured.
This is the off-roader that bridged the gap from the military to the civilian world. With its origins in agriculture like the Unimog, and bearing more than a passing resemblance to the Jeep, the Series 1 Land Rover went from humble origins to open up the planet like no other vehicle. The British Rover Company had built its reputation on luxury cars. But in post-war England, such vehicles were hardly in demand. To remain in business in a time of austerity, a short-term solution was needed. And while driving his war surplus Jeep on his rural property, Rover's chief engineer, Maurice Wilkes, hit upon the idea of designing a civilian version of the wartime workhorse. Within months, his idea was approved, and the first series of the Land Rover was rushed into production. With two ranges of gear, too high and too low, the original Land Rovers used a transfer box to make maximum use of engine torque.
Generally, the biggest difference between four-wheel driving engines and high-performance car engines is that a four-wheel driving engine is centered around torque and reliability, where that four-wheel drive is not going to be necessarily going very fast, but it needs to have a lot of strength, essentially, to get up steep cliffs or over boulders. And it also needs to not break down when you're in the middle of the desert.
With an immensely strong box section, steel chassis, and waterproof wiring, these vehicles willingly went anywhere and kept on going. Despite its minimal comfort levels, this simple and robust 4x4 found its place not just with rural buyers, but with the new breed of off-road adventurer. And with ready markets across the British Commonwealth and former empires, Land Rovers exported to Africa, the Middle East and Australia, giving access to uncharted and inhospitable parts of the world like no vehicle before. The demands of both civilian and military drivers for enhanced off-road performance culminated in a car that served in both worlds: the high-mobility, multi-purposed wheeled vehicle, better known as the Humvee.
As an SUV, it is huge. It fits right in America because everything is big in America. It would literally cast a shadow over the rest of the traffic.
In the late 1970s, the US Army was again looking to upgrade and began seeking a light tactical 4x4 to replace its aging fleet of Jeeps. The vehicle needed to have the latest in off-roading capability and be versatile enough to fulfill the jack-of-all-trades role that had so aptly been served by the Jeep. Of the three companies that presented prototypes, AM General's Humvee won out and entered service in 1984. First entering combat in the US invasion of Panama in 1989, it was the Humvee's widespread use in the Gulf War of 1991 that saw it enter civilian consciousness. With its wide-set machismo, the vehicle's most prominent admirer was former Terminator and future California Governor Arnold Schwarzenegger. So dismayed with AM General's refusal to sell its military vehicle to a civilian, he lobbied the company to produce a civilian version. And in 1992, it was Schwarzenegger who became the first owner of a civilian Humvee, known as the Hummer. Larger and with a much wider track than a Jeep, the Humvee maintained the Jeep's low profile, but managed to nearly double its ground clearance by raising the drive shafts and fitting the axles towards the top of the wheel, rather than in the centre.
Well, it is huge to start with. It's got a lot of ground clearance, so it can get over boulders, and a really solid four-wheel drive system that allows it to plough through the bush and mud tracks anywhere it wants to go.
With torque biasing differentials at the front and rear, each output shaft to the wheels is able to rotate at different speeds. So when a decrease in torque is detected in a wheel slipping over loose terrain, increased torque is transferred to the opposite wheel, boosting power on one side of the car to compensate for a loss of traction on the other. While its off-road prowess is beyond question, the Hummer's excessive size and poor fuel economy has made its transition to civilian life a controversial one. Also controversial when introduced in 1980, BMW's R80 GS went on to inspire a new style of motorcycle for a new style of riding, adventure touring. When first released, this motorcycle bucked the trend towards specialized machines by aiming for a crossover skill set. At the time, few thought a two-wheeler was able to incorporate off-road capability with on-road performance. Today, after more than 30 years on the market, the ongoing popularity of the GS series has silenced its initial detractors. Among a host of design innovations, the GS helped pioneer a new style of motorbike suspension.
You've got long suspension travel, you've also got a 21-inch front wheel, and that also helps to absorb bumps, particularly if you're on the off-road surfaces.
Tough and surprisingly smooth, the GS was a revelation for two-wheel touring enthusiasts and more. Like the early four-wheel drives that preceded it, it was the versatility of the GS that saw it exceed expectations. The first successful production bike to provide off-road guts, on-road speed, and everyday practicality. The GS reinvigorated motorcycle design, taking bikes back to their roots as the original go-anywhere vehicles.
And this is Wendy Lindstrom from Oakland, battling his way up that terrific 76% grade. Come on, you Wendy! And he makes it in 8 3/5 seconds.
Smaller and lighter with a greater power-to-weight ratio. From their very inception, motorbikes had the go-anywhere advantage over cars. Like their four-wheeled counterparts, the motorbike cannot be traced back to a single idea or invention. Instead, they represent the combined and ongoing work of engineers and inventors around the world. But there is one revelation that made mass production possible: the Didion Bouton engine.
I wonder what would happen if this fella let go. Fall off, I guess.
Invented in 1895 by French engineers Jules Albert Didion and Georges Bouton, the single-cylinder four-stroke engine generated half a horsepower, a remarkable achievement for the time. Compact, lightweight and high revving, the Didion-Bouton engine set a benchmark that motorcycle manufacturers the world over would copy and build upon. With the onset of the First World War in 1914, cars were not yet able to provide dependable off-road transport, and it was the motorcycle that filled the gap. Phasing out the horse, motorcycles were used extensively by both sides of the conflict to gather reconnaissance, deliver communications, and even engage in combat. Following the Second World War, many veterans, particularly in America, gravitated towards motorbikes as a substitute for the thrills and danger of wartime action, finding camaraderie in outlaw motorbike gangs. And there was one bike that transitioned from an admirable service in the military to an image of rebellion on the road. Few vehicles of any kind can boast of an iconic status quite like the Harley-Davidson. Celebrated in pop culture and supported by the company's own clever marketing, these bikes carry with them an aura of bad boy mystique, American individualism, and of course, power. Barely a decade old when the First World War began, the conflict had a defining impact on the Harley-Davidson company. Dedicating itself to the production of military motorbikes, when hostilities ended in 1918, more than half of the US Army's estimated 20,000 bikes were Harley-Davidsons. This translated to a market of returned soldiers already familiar with and fond of the brand. And by 1920, Harley-Davidson had grown to become the world's largest motorcycle manufacturer. Instantly recognizable by the unique throaty rumbling of their engines, Harley-Davidson have largely remained true to a basic engine formula centered around an air-cooled V-twin engine with its cylinders set at a 45-degree angle. With their long piston stroke, Harley engines are low revving and provide plenty of torque.
Harley-Davidsons make a very distinctive sound due to their V-twin engine layout, where there are two cylinders aligned in a V configuration that give a very lumpy sound as the two combustion events happen close to each other, and then there is a break before they happen again. So rather than having the power coming down like this, sounding nice and even, they go bang, 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 bang.
Part of the feel and part of the rawness of that engine is what you feel, and that is what makes people either really not like them or like them a lot.
Because of their big engines, Harleys tend to be big bikes, and this made them ripe for customization. Starting in California in the late 1950s, the desire for faster bikes resulted in the chopper. Stripping motorcycles of all unnecessary parts, DIY enthusiasts took to chopping up factory frames and welding them back together to produce lower and lighter vehicles capable of greater speed. The characteristic stretching out the front rakes may have sacrificed the bike's low-speed handling, but provided truer steering when traveling at speed. Harley-Davidsons provided the basis for some of the most recognizable choppers, and the craze had its influence on the style of bike the company went on to produce. But whether riding a factory-built Harley-Davidson or a customized chopper, the anti-authoritarian image remained the same. Debuting in 1970 as the XS1, the Yamaha XS650. While Japanese bikes had largely focused on more utilitarian offerings than Western manufacturers, the 650 was a stylish departure from this tradition and sought to take on the Western firms at their own game. It also marked Yamaha's entry into producing four-stroke engines. While the Yamaha Motor Company had staked a reputation on two-stroke engines, in 1970, the XS650 took the risk, branching out in an effort to match the four-stroke offerings of its competitors.
In four-stroke engine, you have valves that controls precisely the amount of air going in, and exhaust gases coming out. So to produce more power, even in motorbikes, you do need 4-stroke engine.
And Yamaha's engineers were up to the challenge. Having collaborated on the high-performance Toyota 200 GT car, their 4-stroke credentials were proven, and it was a scaled-down version of the Toyota's engine that made it into the 650. Affordable, reliable, and enjoyable, the XS650 was a groundbreaking bike for Yamaha, spawning a 13-year production run and a particularly devoted following among flat-track racers. And it was racing that proved the technical triumph of Japanese bikes to the world. From the early 1960s, the big four Japanese manufacturers, Honda, Kawasaki, Suzuki, and Yamaha, became the dominant force on the racing circuit, with bikes offering more power and better performance than their American and European rivals.
After the Second World War, Japanese engineers were banned from producing aircraft. They went to the automotive industry, and that's where the Japanese basically started producing motorcycles.
Success on the track translated into success on the sales floor, with factory-bred racers available to a power-obsessed public at a competitive price. But for all the thrills of enhanced acceleration and knee-dragging cornering on the road, the true go-anywhere nature of motorbikes is seen when they leave the ground altogether. Freestyle motocross does not compete with speed, instead focusing on the daredevil skills of riders as they seek to outdo each other in gravity-defying stunts. Emerging from off-road dirt bike racing, today this high-flying, high-adrenaline spectacle is one of the most popular extreme sports in the world.
The power they produce in such a light, small capacity, and then the amount of travel the suspension has would probably be the two main key components that set those bikes apart from other bikes in the industry.
Not requiring the fine engine tuning of racing vehicles, the bikes here are essentially ridden as stock, so long as the riders can grab a handful of throttle for rapid acceleration over a short distance. The rest is up to their own ability and courage. Lightweight dirt bikes running on small to medium displacement, 2-stroke engines are favoured, and again, it is the offerings of the Japanese manufacturers that are most prevalent. Modifications are minimal, removing seat foam to give a wider range of motion, or adding a steering stabilizer to keep the front wheel straight when letting go of the handlebars. Other than that, the bikes, with their strong suspension and high traction tyres, are largely factory standard, meaning that just about anyone, provided they have a suitable launching point and no fear of heights, can take these versatile two-wheelers off-road and into the air. Unveiled as a part of BMW's vision for the next 100 years, the Motorrad is the motorbike of the future. A future where helmets and leather are a thing of the past. With self-balancing wheels and gyroscopes serving to keep the bike upright, even at a complete standstill, the stability of this concept vehicle is set to eliminate the need for safety gear as well as a kickstand. And with a degree of autonomy in its driver-assisting technology, a late reaction from the rider will see the bike take over to balance itself out, essentially making it an anti-crash motorbike. A visor replaces both the helmet and the instrument cluster, with its integrated screen providing a heads-up display. Controlled by the rider's eyes and simple finger gestures, these data goggles collect information from the environment and feed back as little or as much detail as the rider desires. When riding, the Boxer engine extends out from the sides of the bike, improving aerodynamics and weather protection. And it's promised to be emission-free. But perhaps the bike's most revolutionary aspect is its carbon fibre flex frame. Changing shape in response to the movement of the handlebars and relaxing or stiffening depending on speed, the flexible structure allows maneuverability without bearings and joints. Integrating form and function, The Motorrad is steering the future of motorbikes in a new direction. In the here and now, for many work vehicles to have go-anywhere freedom and functionality, size matters. This is the Caterpillar Series 7. Serving in mining and heavy-duty construction, these ultra-class trucks are among the biggest ever built. With earth-moving machinery growing larger and more efficient, hauling vehicles are needed to keep pace. In 1997, Caterpillar, with the then latest computer-aided design technology, engineered the original Series 7 vehicles to offer the greatest payload capacity of any mechanical drive-haul trucks.
The 797F truck is an amazing vehicle, and only approaching to this vehicle in a mine site, you can have a clear idea of its huge dimensions. It is 15 meters long, almost like a coach bus, and is 9.5 meters wide and 6.5 meters high.
Nearly 8 meters tall and 10 meters wide, the latest Series 7 weighs a staggering 690 kilograms. And that's while empty. With a suitably enormous pillar-like hydraulic suspension system, the real heavy lifting is done by the 6 specially designed Michelin radial tyres, each weighing over 5 tons. All this powered by a turbocharged 20-cylinder 4,000 horsepower engine.
The 797F was developed because the machines that are used in a mine site to dig and to load the material are becoming bigger and bigger. They can load up to 100 tons of material in just one single scoop.
Owing to the Caterpillar's exceptional size and weight, they cannot be driven on public roads. Delivered to site in pieces on the back of 12 semi-trailers, assembly requires a team of 7 Caterpillar mechanics working around the clock for 20 days.
One of the most exciting things about this truck is to climb the ladder in front of it. And when you reach the cab, the view that you have from this lever that is like staying 2 stories off the ground is amazing.
A huge truck with a huge role to play, the Series 7 range works in the service of even bigger vehicles. Vehicles like this. The Bagger 288.
These mammoth excavating plants combine the efficiency of conveyors with the utility of bucket excavation in a single gigantic earth-moving machine with relatively few continuously moving parts. The Bagger 288 can move the equivalent of 30 football pitches in the space of an hour.
A mobile strip mining machine, the Bagger 288, is truly mountainous, a handy attribute when your job is literally moving mountains. Taking 5 years to design and manufacture, and another 5 to assemble, upon completion in 1978, the Bagger took the record as the heaviest land vehicle in the world. After 23 years of service at Germany's Hambach coal mine, the giant excavator had exhausted supply and needed to make the move to a new mine some 22 kilometres away. Travelling at a leisurely 10 metres per minute, this equated to a 3-week journey. Sitting atop 3 rows of 4 Caterpillar track assemblies, each 3.8 metres wide, the weight of this epic excavator is incredibly well distributed. Nonetheless, special grass was sown ahead of the Bagger's journey to prevent it from sinking. Today, the Bagger continues work at its new home, where its coal-moving efforts help produce 15% of Germany's annual power supply. Already common in big industrial machines, driverless technology is poised to make it onto the highways, promising to enhance safety and efficiency in some of the largest street-legal vehicles. Mercedes-Benz is accelerating the transition with its future truck 2025.
You have virtually all of the
automotive manufacturers now striving to introduce greater and greater levels of autonomy over the next decades.
With eyes in the form of radar sensors, Future Truck makes real-time decisions based on its immediate vicinity. And with data gathered from other connected vehicles and satellites, it makes accurate predictions along its entire route.
The car might still want you to be available to take control of the car if it runs into a situation that it doesn't know how to deal with. Then from there we go to mind-off driving, where you can for the first time really sit back and not worry about it. When the car takes over, you're not expected to be available anymore.
On the highway, the system operates much like autopilot on a plane, taking over the controls for the monotonous hours of long-haul transport, with the human driver free to relax or perform other tasks. When the truck leaves the highway, the driver is back behind the wheel, steering the Future Truck to its final destination. Before autonomous technology changed the way we thought about driving, this vehicle had been there and done that.
That popular little car, the Mini, is in the news again.
The Mini is a tiny car with a towering legacy, and after the Ford Model T, this ultra-compact economy vehicle is regarded as the second most revolutionary car of all time. Produced by the British Motor Corporation and its successors, this icon of 1960s pop culture was lent an enduring appeal thanks to its uncanny knack of going or fitting in surprising places. Built in response to the fuel rationing imposed by the 1956 Suez Crisis, which saw Europe cut off from its Middle Eastern oil supply, the Mini has transcended its purpose-built origins with a design so endearing it has barely changed from across 40 years of production. The key to Mini's mold-breaking success was its transverse engine layout. While previous cars with sideways-mounted engines had been limited to small two-stroke motors, Mini designer Alec Issigonis saw room for improvement. Incorporating the original Mini's transmission into the engine's oil sump freed up the extra space needed to fit a bigger, more powerful four-cylinder engine above the front wheels. And by utilising front-wheel drive, there was no need for a drive shaft, allowing 80% of the car's flat floor plan to be used for passengers and luggage. This layout brought a surprising amount of room and a respectable amount of power to an otherwise unassuming vehicle, influencing a generation of car makers. Since the Mini, almost all small front-wheel drives use a version of Issigonis' configuration. With its 10-inch wheels placed on each corner of the car in a bulldog stance, and with a suspension system of compact rubber cones rather than conventional springs, the low-set front-wheel driving Mini handled like a go-kart. While Issigonis was initially reluctant to depart from the Mini's image as an everyman's car, he came to collaborate with race car builder John Cooper. The result was the first Mini Cooper, with a souped-up racing-tuned engine putting big power into the little car. The Mini Cooper claimed 3 victories at the Monte Carlo Rally, helping cement the vehicle's reputation as a game-changer. Production of the original Mini continued into the year 2000, but its legacy still lives on. BMW took over the Mini marque, and to this day are producing cars inspired by Issigonis' design, a design that changed the way people thought and perhaps more importantly, felt about small cars. Big or small, in the quest to go anywhere, sometimes wheels just aren't enough. With its origins traced back to the mid-19th century, the continuous track has enhanced the off-road capability of wheels by increasing traction and decreasing ground pressure. Contacting the ground only with their bottom portion, wheels concentrate their grip and their weight on a relatively small surface area, limiting traction and increasing the risk of sinking. Contacting a far larger surface area, the continuous track distributes a vehicle's load across the entirety of that area, improving grip and allowing travel over more unreliable surfaces. Employed in heavy off-road machinery such as the Bagger 288, the continuous track's most famous application is in tanks. And when it comes to tanks, there are a few more famous than this. the M1 Abrams. Developed during the Cold War, the M1 Abrams is today the principal battle tank, not only of the US Army and Marine Corps, but the armies of Australia and much of the Middle East. The race car of the tank world, the Abrams can approach speeds of 100 kilometres per hour. But because of the risks posed to the crew and the vehicle itself, an engine governor limits speeds to 72 kilometres per hour on-road and 48 kilometres per hour off-road. Nonetheless, the Abrams remains one of the fastest main battle tanks in service, all the more remarkable for the fact that it's also one of the heaviest.
So that tank has a gas turbine engine that, rather than developing thrust via an exhaust nozzle as we do on aircraft to propel aircraft, spins a shaft that via a gearbox drives the wheels and the tracks of the tank. And so what that allows the Abrams to do is very, very quickly bring on large amounts of motive power to drive that tank, that very heavy tank, to very, very high speeds for a tank.
Effectively a jet engine, the Honeywell AGT 1500 offers an increased power-to-weight ratio over a conventional piston engine and takes up less space. Running on anything from kerosene to jet fuel, the gas turbine is also significantly quieter, earning the Abrams the nickname Whispering Death. Quicker and more manoeuvrable than other tanks, the Abrams turbine engine comes with two drawbacks. It drinks a lot of fuel and generates a lot of heat.
There is a heat exchanger system on board the engine of the Abrams tank that allows it to recover some of that waste heat. For a tank, it has the additional advantage, of course, of not rejecting exhaust gases at very, very high temperature that can be easily detected by the adversary. So, of course, if you can take some of that exhaust heat out, you can use it within your engine, within your tank, and it also means that the exhaust flow will be that much cooler, and therefore you can more easily hide your thermal signature.
But tanks aren't made to hide. They are made to fight. And to that end, the Abrams' main weapon is its 120mm M256 smoothbore cannon. Blasting high-velocity, armour-piercing and explosive rounds, the cannon is guided by a cutting-edge fire control system. With sensors monitoring the tank's tilt, its motion and even the wind, the cannon is computer-adjusted to keep targets in sight, allowing the Abrams to fire with accuracy while on the move. Strong and fast, the M1 Abrams is an almost unbeatable tank. For now. In the world of military technology, the battle for superiority never stops, and new innovations are always waiting in the wings. Innovations like this. At the US government's Defense Advanced Research Projects Agency, better known as DARPA, the search to find new transport systems has led to the rise of the machines. Machines that borrow from nature. Rather than reinventing the wheel, DARPA and engineering company Boston Dynamics have turned their attention to the efficient methods of movement developed by animals over 4 billion years of evolution. The Legged Squad Support System, LS3, is in essence a robotic pack horse.
Let's go back to cowboy days when you had your pack horse. That's the same concept, except this thing is a robot that follows you around. It can carry a lot of weight and go up and down terrain and do all those sorts of things. So you don't have to feed it.
The motorised quadruped uses a combination of cameras and laser sensors mounted in its head to negotiate rugged terrain, all while carrying over 180 kilograms of equipment. Intended to relieve the weight burden carried by military dismounts, LS3 was designed to operate alongside ground troops.
They quite literally look like large dogs or mules. Four-legged, and it just follows them around.
Proving itself in field tests, LS3 was ultimately shelved due to noise concerns. But it provided the launching point for the next generation of animal robot. The cheetah. While this running robot may not yet match the speeds of the fastest animal on Earth, it can cover over 12.5 meters per second, making it faster than any human. Coming along in leaps and bounds, animal-inspired technology is set to change the way we think of going off-road. Going off-planet, more traditional wheeled vehicles have made remarkable achievements.
So we kind of take advantage of being able to build cars and vehicles on the Earth. You know, we know friction, we know how it stays, but the lunar dust is drastically different. You know, there's a reason we've always had those pictures of, you know, someone's footprint landing in the moon and that footprint still being there. That's because lunar soil is drastically different than Earth's soil.
While officially named lunar roving vehicles, these cars, taken to the moon on the last 3 Apollo missions in the early 1970s, will be forever remembered with their affectionate moon buggy nickname. Weighing a little over 200 kilograms, these lightweight compact vehicles were folded into 3 parts for storage in the cramped Apollo lunar modules. After assembly on the moon's surface, each buggy ran on a series of 4 electric motors mounted in the aluminium wheels. Producing a total of 1 horsepower, it was enough to clock up a top speed of 18 kilometers an hour in the low-gravity atmosphere. Designed to give astronauts a wider range to explore and collect samples around their landing site, the moon buggy also revitalized a flagging public interest in the Apollo missions, bringing a sense of fun to the lunar surface. Today, the cutting edge of off-planet off-roading is all business.
Order of 11, 12, 13.
Eagle Dodge, you remain strong.
Touchdown confirmed. Receiving.
Touching down on the red planet in August 2012, this is the Curiosity Mars rover. The 4th unmanned NASA rover sent to Mars. The Curiosity is the biggest and toughest of them all.
So you have to build special tires, special traction, special dust filters, because, you know, if you get finely grained dust and it's going to clog up your dust filter, you know, think of how many problems we have just driving into work every day. But then your work is on Mars, and the destination is you not dying, right? You know, it's such a dramatic scenario that these things have to go through. They have to be robust, they have to be rigorous. And I think we take for advantage the fact that some of the Mars rovers have passed a decade.
While previous Mars rovers ran on solar energy, Curiosity runs on plutonium oxide. As the radioisotope decays, it gives off heat, which Curiosity converts to electricity through its thermoelectric generator. Going nuclear also brings more power, and despite being the heaviest of the Mars rovers, Curiosity moves at twice the speed of its predecessors. With a powertrain free of moving parts and a fuel source with a 14-year life expectancy, this nuclear power plant on wheels is set to keep on keeping on. To make sure this is the case, Curiosity utilizes NASA's rocker bogie suspension system. Foregoing axles or springs, this spider-like assembly of jointed titanium tubes is more robust and better balanced. The system allows the rover's 6 wheels, made of aluminium so thin that they flex like rubber, to move independently, maintaining constant ground contact over even the most difficult terrain. This balanced distribution of force provides maximum traction to all wheels at all times. Initially piloted by remote control from Earth, Curiosity has largely switched to autonomous navigation.
You've had rovers robotically going on Mars for over a decade, and I think it's just amazing how well that engineering has come to make that happen. Because they're not designed for a decade. You know, NASA designed something for a definitive mission, usually anywhere between 3 months and a year, but, you know, to get year 7, year 8, year 9, year 10, it's just amazing how well it works.
More independent, more sure-footed, and more powerful than anything before, This Martian workhorse is the model for future Mars missions. Using the same design platform as Curiosity and even a few of its spare parts, the unnamed 2020 Rover upgrade is less a different model and more a different mission. Taking the next step from Curiosity's search for signs of habitable conditions in Mars's past, the 2020 will go searching for signs of life itself. And with a scientific payload that includes an experimental machine for converting the toxic Martian air into breathable oxygen, this vehicle is set to pave the way for humans to make our first interplanetary journey. Back on Earth, the long-held science fiction promise of flying cars is close to becoming reality. Classed as a roadable aeroplane, the transition is, as the description suggests, a hybrid car and plane. In development since 2006, the Transition's 3 prototype models have all been proven in drive and flight tests, and the development company Terrafugia today plans on entering market production by 2020. Designed to fit in a standard household garage, in drive mode, the 2-seater carbon fibre vehicle operates via a typical steering wheel and foot pedals and carries other standard car features such as bumpers and airbags. With a top speed of 110 kilometres per hour and reasonable fuel economy, upon reaching the airport, the Transition really distinguishes itself. Within 1 minute, its electromechanical wings fold out and the rotary 100 horsepower engine transitions to drive a pusher propeller. Provided the driver has a sport pilot license, they can take the twin-tailed light aircraft to an altitude of over 3 kilometres and a cruising speed of over 170 kilometres per hour. In the air, fuel economy takes a nosedive, but the Transition is hardly designed to appeal to conservative motorists. And with the air allowing commuters to travel straight as the crow flies without speed limits, this vehicle of the not-too-distant future is set to create a whole new genre of off-roading. For a flying car that is on sale now, consumers with $500,000 to spare can today order their very own personal air and land vehicle, the PAL V1. Melding aspects of car and helicopter, this Dutch-designed roadable aircraft is far harder to categorise. Driving on 3 large wheels of its tricycle undercarriage, the PAL V1 is able to lean into turns like a motorbike. The PAL V1 can be converted in around 5 minutes to an autogyro, an aircraft that obtains lift from rotor blades and thrust from a propeller. With its unique Rotax dual propulsion engine now powering the propeller, the 2-seater can attain its same land speed of 180 kilometres per hour. Thanks to vehicles like the PAL V1 and the Transition, the future of land-based transport is no longer limited to the land. The quest to go anywhere is an ambition as old as civilization. From the dawn of the motorised age, cars, motorbikes and others that defy labels have sought to provide the power and the wherewithal to take us wherever we needed or wanted to go. Today we are redefining the concept of go anywhere, changing the way we move in order to open up our world in new ways and open up worlds beyond.